When we think of the wonders of the universe, our minds often go straight to planets, stars, and galaxies. But some of the most mysterious worlds out there aren't planets at all. Every moon is like a miniature world with its own story, shaped by ancient collisions, frozen oceans, and strange forces, making them one of the most fascinating frontiers in modern space exploration. In the last few years, new missions and telescopes have revealed just how diverse these natural satellites can be. As we look closer, these mysterious moons remind us that most solar systems are not collections of dead rocks. They are living, changing places, full of secrets still waiting to be uncovered. Plumes on Enceladus. When the Cassini spacecraft first arrived in the Saturn system in 2004, few imagined that one of the smallest moons orbiting the gas giant would soon become one of the most intriguing places in the solar system. Enceladus, a world barely 500 kilometers across, was at first just another icy moon, a bright frozen sphere reflecting sunlight like a mirror. Yet as Cassini began to observe it more closely, something extraordinary was discovered. Beneath its crust of ice, Enceladus was alive with motion. The moon wasn't still or dead. It was venting material into space, forming enormous plumes that sprayed from its south pole. These ghostly jets shimmered in Saturn's faint light, hinting that something dynamic, and possibly even biological, was happening deep below the ice. Cassini's instruments had not been designed to search for life, but its array of sensors turned out to be perfect for exploring these plumes. As the mission entered its later years, the spacecraft performed a series of close flybys, diving through the icy sprays that burst from cracks known as the tiger stripes. These fissures stretched across Enceladus's southern hemisphere, each one a vent into the hidden ocean beneath the crust. At first, scientists were cautious about what they were seeing. Water vapor and ice crystals could have been just surface frost evaporating under sunlight. But as Cassini sampled the material, the data told a very different story. The spacecraft's spectrometers detected not only water vapor, but also salts, simple organics, and traces of carbon dioxide and methane. These were not the signs of a frozen, inactive world. They were the ingredients of a potentially habitable environment. Later flybys also revealed tiny grains of silica suspended within the vapor. On Earth, silica of this kind forms only under specific conditions, usually near hydrothermal vents on the ocean floor where hot water interacts with rock. Hydrothermal activity implied that Enceladus's ocean wasn't just a stagnant pool trapped beneath ice. It was warm, moving, and interacting with a rocky core. It meant that chemical energy could be present, just as it is in Earth's deepest oceans, where hydrothermal vents provide heat and nutrients to entire ecosystems. These are places where life thrives without sunlight, feeding on the minerals and gases bubbling up from the planet's interior. If Enceladus had similar vents, then its ocean could be a natural garden for biology. A world where life might exist independent of any sunlight, surviving in total darkness beneath kilometers of ice. To test this idea, in 2015, the spacecraft swooped within only 49 kilometers of Enceladus's surface, directly through one of the plumes. It was one of the closest encounters ever attempted with a moon of Saturn. During those moments, Cassini's instruments were bombarded with particles, water, ice, and molecules that had been ejected from the moon's ocean far below. The results were astonishing. Not only were the jets rich in organic material, but some of the compounds were large and complex, containing carbon chains much longer than those previously seen on icy worlds. Complex organic molecules are the building blocks of life as we know it. Their presence in Enceladus's plumes meant that nature had been mixing chemicals in its hidden ocean, creating the same kinds of ingredients that might have given rise to life on early Earth. When scientists compared the data to hydrothermal processes on our planet, the similarities were striking. It seemed that at the bottom of Enceladus's ocean, water was seeping into cracks in the rocky core, becoming heated by geothermal energy and rising back up to the ice layer above. This constant cycle of heating, cooling, and chemical reaction could maintain the right conditions for microbial life. One of the most telling discoveries was the balance of hydrogen detected in the plume gas. On Earth, hydrogen serves as a key energy source for certain types of microbes living near hydrothermal vents. Its presence on Enceladus hinted at similar chemical pathways, energy that life could use if it existed there. The ratios of methane, carbon dioxide and hydrogen were particularly interesting because they resembled the byproducts of both abiotic chemistry and biological metabolism. Before Cassini, Mars was considered the most promising target for astrobiology. But Enceladus and Jupiter's moon Europa shifted that focus toward icy worlds with subsurface oceans. Life, it seemed, might not need sunlight or a thick atmosphere at all. It might simply need liquid water, the right chemistry, and an energy source. Cassini's flybys showed that all three exist on Enceladus. The mission had rewritten textbooks. Enceladus, once overlooked, had become a reminder that even the smallest worlds can hold the biggest surprises. The data gathered during those final flybys continues to be studied today. How deep is the ocean? How long has it existed? We do not yet know, but Cassini left us with enough clues to keep searching. The next generation of missions, like the proposed Enceladus Orbelander, may one day return to taste those plumes again, only this time with instruments designed to look directly for life. Europa's ice shell thickness. In the past, scientists estimated Europa's icy crust to be up to 50 kilometers deep, a formidable barrier between the frozen surface and the ocean beneath. Such thickness would make any attempt to reach that ocean incredibly difficult, both for robotic probes and for understanding how surface features form. But the latest observations hint at a far more dynamic world. The thinner the ice, the more likely that the ocean and the surface interact, allowing heat, minerals, and possibly even organic molecules to move between the two layers. That interaction could make Europa's ocean a much more habitable environment than previously thought. The evidence comes from a combination of observations that, when layered together, reveal a more complete story. The Hubble Space Telescope detected faint plumes of water vapor near Europa's southern hemisphere, jets that may be escaping from cracks in the ice, much like those seen on Saturn's moon Enceladus. These plumes are subtle, but they repeat in specific regions, suggesting they come from deeper sources rather than surface frost. If water is indeed venting from beneath the surface, the ice shell must be thin enough in places for cracks to reach the ocean, or at least to pockets of liquid water trapped within the ice. Meanwhile, radar data gathered from Earth-based observatories and older spacecraft flybys has provided a glimpse beneath the moon's surface. Radar waves can penetrate ice and reflect back details about its structure and density. By measuring how those waves bounce and scatter, scientists can infer whether the ice is solid, layered, or mixed with pockets of liquid. They found that certain regions on Europa reflect radar signals in ways that suggest variations in thickness, and even areas where the ice may be only a few kilometers deep. These patches coincide with surface features such as ridges, bands, and chaotic terrain, places where the crust appears to have been pulled apart and then refrozen. Europa's surface is one of the most geologically young in the solar system, with few impact craters and a maze of intersecting lines etched across its plains. These long, winding ridges and dark streaks are believed to result from stresses in the ice shell caused by Jupiter's immense gravity. As Europa orbits its giant planet, tidal forces flex and squeeze it, generating heat within its interior. That heat prevents the ocean from freezing completely and keeps the surface in constant motion. The cracking and shifting seen on the surface are the scars of that struggle between freezing cold and internal warmth. If the ice is indeed thinner, those stresses could have a greater effect, allowing the crust to stretch and tear more easily. In some places, the surface may even briefly melt, forming temporary lakes beneath the ice. Observations from Galileo, which flew past Europa in the late 1990s, hinted at regions where the magnetic field behaved as though it was interacting with salty water near the surface. Combined with newer radar analyses, this strengthens the case that parts of Europa's crust are thin enough for subsurface water to rise close to the top. If the crust is around 15 to 20 kilometers thick, it becomes more feasible for future missions to penetrate it, either through drilling, melting, or sampling material ejected from surface cracks. For scientists searching for signs of life, this could be the key. Any place where the ice connects to the ocean below offers a natural pathway for exploration. Instead of having to dig deep into the ice, a probe could simply fly through or land near these active regions and analyze the vapor and particles they release. NASA's Europa Clipper mission, launched in late 2024, carries a suite of instruments designed to study exactly these features. It will orbit Jupiter and make dozens of close flybys of Europa, using radar to map the ice structure, cameras to examine the surface in detail, and spectrometers to identify its chemistry. The spacecraft will also look for signs of ongoing activity, like the water vapor plumes detected by Hubble. If Clipper confirms that some of these jets truly originate from the subsurface ocean, it would mark one of the most important discoveries in planetary science, proof that the ocean is accessible, at least indirectly, from the surface. Tiny variations in the Moon's gravitational field, measured during spacecraft flybys, can reveal differences in density beneath the surface. When scientists analyzed how Europa's gravity affected the motion of past probes, they noticed subtle shifts that suggested the ice shell might be thinner in some areas and thicker in others. These differences could indicate places where warm upwellings rise from the ocean below, pushing against the ice and thinning it from underneath. Such dynamic processes are similar to those seen in Earth's polar regions, where currents beneath Antarctic ice shelves shape the landscape above. Some of Europa's most puzzling regions, like the so-called chaos terrain, where the surface looks like a jumbled puzzle of broken ice blocks, now make more sense in this context. If the ice is thinner there, it may be breaking apart as warm water wells up, melting and refreezing repeatedly. These areas could mark direct communication points between the ocean and the surface, where nutrients and energy move upward. On Earth, similar processes at the bottom of our oceans support thriving ecosystems around hydrothermal vents. If Europa's ocean behaves in the same way, it could mean that life, if it exists, might not be confined deep below, but could find ways to reach higher layers where future missions might detect it. The idea of a thinner crust also helps explain how Europa's surface remains so young. If the ice shell were extremely thick, geological renewal would be slow. But if it is thin and flexible, tidal heating could continuously recycle the surface, erasing craters and reshaping ridges over millions of years. This constant renewal may even contribute to the faint atmosphere around Europa, which is composed mostly of oxygen created when sunlight and charged particles strike the icy surface. Some of that oxygen might eventually find its way into the ocean below, providing another ingredient essential for life. The more we learn about its structure, the more it feels like a sibling to Enceladus. But Europa's ocean is far larger, perhaps containing more water than all of Earth's seas combined. If its shell truly is thinner, then the boundary between that immense dark ocean and the vacuum of space might be far closer than anyone once believed. For now, scientists can only infer these details from afar, combining data from telescopes, radar, and spacecraft. Future missions might one day send landers capable of drilling or melting their way into these regions, sampling the ice for trapped organics or biological signatures. Even without drilling, orbiters could study the plumes, if they exist, and analyze the particles for amino acids, salts, or other complex molecules. If the crust is indeed thinner, the chances of finding such traces rise dramatically. It means that Europa's ocean is not locked away in unreachable depths. It might be just beneath our reach, waiting to be explored. Ganymede's magnetic field dynamics. Ganymede, the largest moon in the solar system, is even bigger than the planet Mercury. Unlike any other moon, it possesses its own magnetic field, a miniature magnetosphere that stands against the vast power of Jupiter's. For decades, this feature puzzled scientists. How could a frozen moon, with an icy surface and distant from the sun's warmth, sustain an active magnetic field like Earth's? The answer, it turns out, lies deep beneath its surface, and NASA's Juno spacecraft is now beginning to uncover the secrets of what's happening inside this massive world. When Juno arrived at Jupiter in 2016, it was designed primarily to study the planet itself, its atmosphere, gravity, and magnetic environment. But as the mission progressed, the spacecraft's orbit brought it close enough to Ganymede to gather detailed data about the Moon's magnetic and plasma interactions. These flybys, some of the closest ever made to Ganymede, gave scientists a fresh look at how the Moon's magnetic field behaves within Jupiter's colossal magnetosphere. What they found was a dynamic and complex relationship, one where Ganymede's own magnetism dances within a sea of Jupiter's charged particles, producing auroras, electrical currents, and subtle shifts that reveal what's going on far below its icy crust. Ganymede's magnetic field was first discovered by Galileo in the 1990s. At the time, it was a surprising find because no other moon had ever shown such a feature. Most planetary magnetic fields are generated by the motion of conductive fluids, usually molten metal, inside a planet's core. On Earth, for example, the spinning of liquid iron in the outer core generates our global magnetic field. For Ganymede to have something similar meant that its interior had to be at least partially molten and still active. But scientists were unsure how that could be possible. Ganymede is far from the Sun. Its surface temperature drops below -160 degrees Celsius, and it's been bombarded for billions of years by Jupiter's radiation. Logic suggested it should be frozen solid. As Juno measured fluctuations in Ganymede's magnetic field during its flybys, it recorded variations that depend on how Jupiter's magnetic environment sweeps past the Moon. These measurements indicate that Ganymede's internal magnetic field isn't static. It's actively interacting with Jupiter's, constantly reshaped by the planet's immense forces. At times, magnetic lines from both bodies reconnect and form loops, triggering bursts of charged particles that spiral along the field lines. These interactions create auroras on Ganymede's surface, bands of light that ripple faintly across its polar regions, invisible to the naked eye, but detectable by instruments sensitive to ultraviolet radiation. These auroras are diagnostic tools. By studying how they move, scientists can infer the strength and direction of Ganymede's internal magnetic field. Hubble Space Telescope observations, combined with Juno's close-range data, show that the auroras rock back and forth in rhythm with Jupiter's magnetic field. That gentle oscillation reveals how the Moon's magnetic bubble is distorted by Jupiter's overwhelming influence. From those distortions, researchers can deduce the characteristics of the liquid metal core that generates Ganymede's field, its size, composition, and even how it circulates. Current models suggest that Ganymede's core is primarily made of liquid iron mixed with sulfur, a combination that remains molten at lower temperatures than pure metal. As this liquid core rotates within the Moon, it creates electric currents that power the magnetic field. Surrounding this metallic center are rocky layers and a thick mantle of high-pressure ice. But the new data imply that these ice layers might not be uniform. Between the solid ice above and the rocky core below could lie layers of slush or even salty water, conducting electricity and influencing how the magnetic field behaves. In other words, Ganymede may have multiple subsurface oceans stacked between layers of different types of ice, an intricate internal structure unlike anything else in the solar system. What keeps the core molten, though, remains a key question. One explanation is tidal heating. Even though Ganymede's orbit around Jupiter is relatively stable, it still experiences slight gravitational flexing due to the other nearby moons, Io and Europa, which tug on it in rhythmic patterns. This gravitational dance could produce enough heat deep within Ganymede's core to maintain a partially molten state. Over billions of years, that internal warmth would allow the metallic core to churn slowly, sustaining the dynamo effect that produces its magnetic field. As Juno flew over the Moon, its instruments also detected variations in the density of plasma near the surface. These fluctuations hinted at something unexpected. Ganymede's magnetic field may not only be generated internally, but also modified by electrical currents flowing through its outer ice layers. The presence of salts or ammonia within the ice could make those layers slightly conductive. If liquid water pockets exist there, they could carry electrical currents strong enough to affect the magnetic field's behavior. That means Ganymede's interior could be even more dynamic than previously thought. The grooved terrain seen across Ganymede, vast bands stretching for thousands of kilometers, might be the visible scars of these internal movements. In this way, Ganymede might resemble a frozen, slower version of Earth with its own form of plate activity and resurfacing. Unlike Europa or Callisto, which are constantly bombarded by charged particles trapped in Jupiter's magnetosphere, Ganymede's magnetic bubble deflects much of this radiation. The result is a thin atmosphere of oxygen, produced when surface ice is split apart by radiation and sunlight. It's an extremely tenuous layer, but it demonstrates that Ganymede's environment is complex. The interaction between Ganymede's field and Jupiter's magnetosphere creates a symphony of charged particle flows and electromagnetic waves. Juno's instruments have picked up whistlers and radio emissions, patterns of radio noise that travel along magnetic field lines. These signals carry information about the density and composition of plasma around the Moon. Some of these emissions are surprisingly similar to those heard in Earth's own magnetosphere, suggesting that despite the differences in scale, the same physical principles govern both environments. Ganymede may still be evolving, driven by internal heat and shaped by the immense magnetic and gravitational forces surrounding it. Understanding how its core operates and how it interacts with the icy shell above could reveal not only why Ganymede alone possesses a magnetic field, but also how magnetic activity can persist in other icy worlds. If Ganymede can maintain a liquid core and internal motion despite its distance from the Sun, then similar processes might occur in other large moons throughout the outer solar system. Titan's methane cycle revisited. Shrouded in a dense orange haze, Titan, Saturn's largest moon, had long resisted attempts to see its surface. Early observations showed only a smooth, featureless sphere, leaving scientists unsure what lay beneath the thick atmosphere. But as the Cassini spacecraft's radar and infrared instruments began to peer through the clouds, a new kind of world emerged. Over the course of Cassini's 13 years around Saturn, Titan became one of its most studied targets. The spacecraft's instruments mapped nearly the entire Moon, revealing mountains, dunes, rivers and lakes, all sculpted not by water, but by liquid hydrocarbons. Methane and ethane, existing as gases on Earth, act as liquids under Titan's frigid conditions. The temperature there hovers around -180 degrees Celsius, cold enough for these compounds to condense and flow. Cassini's radar showed vast seas near the poles, glistening lakes and even shorelines where waves might lap against frozen ground. It was the first time liquid had been found on the surface of another world. Just as water evaporates, condenses and rains down on Earth, methane and ethane do the same on Titan. Cassini's instruments recorded changes in cloud patterns over the years, and infrared images showed bright spots forming and fading in the atmosphere, likely signs of methane rainstorms. The spacecraft even caught evidence of rain-darkened surfaces that later brightened again as the liquid evaporated. Titan's skies, it turned out, had weather. Titan's seasons are long and slow, lasting more than 7 Earth years each, because Saturn takes nearly 30 years to orbit the Sun. During Cassini's mission, the spacecraft observed Titan transition from northern winter to summer. As the seasons shifted, so did the weather. Clouds moved from one hemisphere to the other, following the sunlight. In the southern hemisphere, Cassini once observed large, dense clouds forming rapidly, stretching thousands of kilometers across. When those clouds dissipated, radar images showed new dark streaks on the surface, possible rainfall marks. Later, similar activity appeared in the north as it warmed, where Titan's largest seas, Kraken Mare and Ligeia Mare sit glimmering near the pole. These changing conditions hinted at a global methane cycle, one that behaves in many ways like Earth's hydrological system. Sunlight heats Titan's surface slightly, causing methane to evaporate and rise into the atmosphere. High above, it condenses into clouds that drift and merge, eventually releasing rain that carves channels into the icy ground. Rivers of methane and ethane may flow for hundreds of kilometers before emptying into polar lakes and seas. Some regions even show branching river networks and delta-like formations, clear evidence that liquid has flowed repeatedly over time. Yet, unlike Earth's water cycle, Titan's methane cycle faces a mystery. Methane in the atmosphere should break down under sunlight over millions of years, forming heavier hydrocarbons and eventually depleting the gas entirely. But Titan's atmosphere is still full of methane today. That means something must be replenishing it. Cassini's data suggests that methane could be seeping up from the interior, perhaps through cryovolcanoes. Ice volcanoes that release cold slurries of water and hydrocarbons instead of molten rock. If so, Titan's surface might still be geologically active, with methane continually bubbling up from underground reservoirs or being produced through chemical reactions in its crust. As ultraviolet light from the sun strikes methane, it triggers complex reactions that produce long-chain hydrocarbons and other organic molecules. These particles form a thick haze that drifts down through the air, coating the surface in organic material. Some of these compounds, acetylene, ethane, benzene, and others, are the same kinds of molecules that, on early Earth, might have contributed to the formation of life. Titan, in this sense, offers a frozen snapshot of chemical processes that could have once taken place on our own planet billions of years ago. Beneath its icy crust lies a global ocean of water mixed with ammonia, likely tens of kilometers below the surface. Above that, the active methane weather system creates an entire secondary world, one where rivers and lakes exist, but in a chemistry utterly foreign to life as we know it. Scientists began to ask whether complex organic reactions could occur within Titan's lakes or on its surface, potentially creating prebiotic molecules, the building blocks of life, without any liquid water at all. This question will guide the next great mission to Titan, NASA's Dragonfly. Planned for launch in the 2030s, Dragonfly is unlike any previous spacecraft. It's not an orbiter or a lander, it's a rotorcraft, a nuclear-powered drone designed to fly across Titan's surface. Because the Moon's atmosphere is thick and gravity is low, flight is relatively easy there. Dragonfly will use this to its advantage, hopping from one location to another, exploring different terrains over hundreds of kilometers. Laboratory experiments on Earth have shown that under Titan-like conditions, organic molecules can combine into more complex structures called tholins. These substances are thought to cover much of Titan's surface, giving it its dark orange hue. Dragonfly's instruments will analyze these tholins to see how they form and whether they can interact with other compounds to produce amino acid precursors or other molecules relevant to biology. Cassini already gave hints of this complexity through its spectrometers, which detected traces of heavy organics in the upper atmosphere. Some of these compounds appeared to be large, chain-like molecules, unexpected for such a cold world. They form as smaller hydrocarbons merge and fall toward the surface, where they may accumulate in layers over time. If energy sources like lightning, ultraviolet light, or geothermal activity can trigger further reactions, Titan might host a rich organic chemistry, cycling through stages similar to the early Earth's prebiotic soup, but with methane instead of water as the solvent. Titan's lakes and seas remain central to this mystery. Cassini's radar measured their depth and composition, finding that some are composed almost entirely of methane, while others have higher concentrations of ethane and nitrogen. The distribution of these lakes also appears seasonal. During northern summer, evaporation increases, shrinking some lakes and thickening clouds overhead. During winter, condensation and rainfall replenish them. These cycles may even create localized weather patterns, including storms and possibly lightning, though no lightning has yet been directly observed. Another intriguing clue came from the reflection of sunlight off the lakes, a phenomenon known as specular reflection. By analyzing these reflections, scientists confirmed that the surfaces were incredibly smooth, consistent with liquid hydrocarbons. Some of the reflections also varied over time, suggesting changes in the liquid levels or even the movement of small waves. It's possible that winds on Titan, though weak compared to Earth's, can stir the seas. Titan challenges the definition of habitability. It shows that the universe may host many forms of chemistry capable of complexity, even under conditions utterly hostile to humans. If Titan's surface chemistry can create molecules that mimic the early steps toward life, it suggests that biology might arise in many different ways across the cosmos. Callisto's internal structure. Callisto circles Jupiter at a distance far enough to avoid the gas giant's punishing radiation belts, allowing its surface to endure in almost pristine form for billions of years. When scientists study Callisto, they're essentially looking back into the earliest history of the solar system, preserved in ice and rock. Data from spacecraft like Galileo, and more recently from refined gravitational models, have revealed that Callisto's internal structure is more complex than expected. It isn't a simple frozen sphere, but a layered world of rock and ice arranged in concentric shells. Beneath a surface battered by countless impacts lies a mixture of water ice and silicate rock, gradually blending toward a denser interior. However, unlike Ganymede or Europa, there's no sign of a molten core or significant heat production. The models show that Callisto's heat flow is extremely low, too low to sustain large-scale convection or active geology. Its energy comes mostly from what little remains of its formation and from the radioactive decay of elements trapped within. Over time, even that meager heat has faded, leaving the moon frozen almost solid. This lack of internal warmth means that Callisto's surface has barely changed since it first formed. Every crater, ridge, and impact basin tells a story of violent beginnings that ended billions of years ago. Unlike Europa's shifting plains or Titan's evolving weather systems, Callisto's face is one of stillness. Its craters overlap in dense, chaotic mosaics, so numerous that they seem to erase each other. No major resurfacing has smoothed them away, suggesting that for nearly 4 billion years, Callisto has simply existed, orbiting Jupiter in cosmic silence. As Jupiter's immense magnetic field swept past the Moon, it induced weak but detectable signals from within Callisto itself. These magnetic anomalies hinted that some electrically conductive layer might exist beneath the crust. On Earth or even Europa, that would suggest the presence of a salty liquid ocean. Could Callisto, too, hold a hidden layer of liquid water deep inside its icy mantle? Callisto's cold surface temperature, around 120 Kelvin, would make any liquid water unlikely. Yet models show that pressure and the presence of ammonia or salts could prevent total freezing, even with limited heat. Deep inside, perhaps 100 to 150 kilometers down, there may be isolated pockets or layers where liquid still survives. These would not form a vast ocean like Europa's, but small, scattered reservoirs locked between rigid layers of ice and rock. Callisto's layers never fully separated by density. Instead of a clean boundary between rock and ice, there's a slow transition, like a frozen slurry. This incomplete separation implies that Callisto never generated enough heat to fully melt and reorganize itself. It formed gently, perhaps capturing material slowly in Jupiter's outer regions, avoiding the violent tidal heating that reshaped Europa and Ganymede. The proportions of ice and rock, the distribution of volatile compounds, and even the trapped gases within its crust may preserve the conditions that existed when Jupiter was still gathering its satellites. In this sense, Callisto is like a fossil moon. The European Space Agency's JUICE, or Jupiter Icy Moons Explorer mission, will perform multiple flybys of Callisto before focusing on Ganymede. Its instruments will measure gravity, magnetic fields, and surface composition in unprecedented detail. These observations could confirm whether the faint magnetic signals truly point to an underground liquid layer, or if they arise from something else entirely. Callisto's low radiation environment also makes it a potential candidate for future human exploration, a stable base of operations in the Jovian system, far from the deadly belts that encircle Europa and Io. Over time, cosmic radiation and micrometeorite impacts have darkened the surface ice, giving Callisto its dusky brown-grey color. The chemistry of its crust, revealed by infrared spectra, shows carbon dioxide frost and traces of complex organics, compounds that likely formed through radiation-driven reactions. They aren't signs of life, but they do show how simple molecules can evolve chemically, even in the absence of internal heat or sunlight. Callisto's deep coldness is what makes it so scientifically valuable. It's a control case for studying how planetary materials behave in the deep freeze of outer space. Each crater basin, each faint ridge, each layer of buried ice offers information about conditions billions of years ago. When considering the potential for subsurface water, scientists often weigh two competing ideas. On one hand, Callisto's extremely low heat suggests that any internal liquid must be small and localized. On the other, even those small pockets could persist for billions of years, if insulated by thick ice and mixed with anti-freezing chemicals like ammonia. The persistence of such hidden reservoirs would make Callisto a rare example of long-term water stability without active heating. It wouldn't likely support life, but it might show how chemical complexity can survive deep within frozen environments. These insights feed into broader questions about habitability. If a world as cold and ancient as Callisto can still hold traces of liquid water, then the boundary of where life-friendly conditions might exist stretches much farther than once assumed. Callisto as a survivor. It is not dynamic, but it is not dead either. It is a moon caught in permanent twilight between formation and decay. Its heat may be gone, its geology long frozen, but its presence remains vital for understanding how worlds begin and what they become when time has slowed them to near stillness. Io's volcanic resurfacing rates. Among all the moons in the solar system, none rival Io's violent beauty. It is a world of fire orbiting within an empire of ice. Where Europa, Ganymede and Callisto preserve ancient calm, Io lives in constant upheaval. Every square kilometer of its surface bears the marks of eruptions so frequent and powerful that they erase craters faster than they can form. It is the most volcanically active body known. The first close look at Io's fury came from Voyager 1 in 1979, when scientists saw an enormous volcanic plume rising hundreds of kilometers above its surface. This was the first active volcano observed beyond Earth. It shattered the assumption that small, distant moons were cold and inert. Later missions confirmed that Io's activity wasn't a fleeting event, but a continuous, global phenomenon. Nearly every observation since has captured new changes: fresh lava flows, glowing hotspots, or entire regions transformed between flybys. Unlike Earth, Io's volcanism is not driven by radioactivity or leftover heat from its formation. Instead, its molten heart is kept alive by tidal heating. The process is relentless, transforming the moon into a literal tidal engine of molten rock. Recent observations have given scientists a new way to measure how quickly Io's surface is being reshaped. Infrared telescopes on Earth, combined with Juno's close flybys, allow researchers to track volcanic activity almost in real time. Massive lava lakes hundreds of kilometers wide pulse with heat as molten material wells up and cools in repeating cycles. Some regions, like Loki Patera, Io's largest known lava lake, appear to undergo resurfacing events every few years, with brightening infrared signals marking waves of molten lava overturning the surface. Others show fresh eruptions that bury older terrain under flows that can stretch for hundreds of kilometers, erasing old features within months. A single eruption on Io can release more energy than all Earth's active volcanoes combined. These outbursts create fountains of molten material that spray into space before falling back as volcanic snow. Some plumes rise more than 300 kilometers high, forming massive rings that encircle the moon. When sunlight hits these volcanic clouds, they glow faintly, tracing arcs of gas that briefly shimmer against Jupiter's shadowed bulk. Instruments on board Juno have captured these plumes in ultraviolet and infrared wavelengths, showing not only their size, but their chemistry, rich in sulfur dioxide, silicates, and traces of sodium and potassium. These materials give Io its surreal, multicolored surface, painted in yellows, reds, and whites that shift constantly as new eruptions occur. Estimates suggest that its crust is completely resurfaced every 1 to 2 million years, an incredibly short time on a planetary scale. On Earth, large regions remain unchanged for hundreds of millions of years, but on Io, lava and sulfurous frost continually bury and rebuild the landscape. Old impact craters vanish almost as soon as they form, replaced by new flows and deposits. In this way, Io's surface is geologically young, even though the Moon itself formed more than 4 billion years ago. Data from Juno's instruments, especially the Jovian Infrared Auroral Mapper, or GIRAM, have revealed that Io's volcanism is far more dynamic than once believed. By mapping heat signatures across its surface, scientists can see eruptions in various stages of activity. Some areas remain hot for years, suggesting sustained lava lakes. Others flare suddenly and cool just as quickly, marking explosive eruptions that eject vast amounts of material into space. Juno's magnetometer has also recorded how Io's plumes interact with Jupiter's magnetosphere, creating streams of charged particles that light up the giant planet's auroras. These electrical connections form one of the most striking planetary relationships in the solar system, a literal power line stretching between a moon and its planet. The exact depth and composition of Io's magma ocean are still uncertain. Some models suggest a global layer of partially molten rock beneath the crust, while others point to localized magma reservoirs feeding specific regions. Understanding these structures is crucial for determining how Io maintains such high levels of activity over billions of years without cooling completely. Why do some regions remain relatively quiet for decades, while others erupt repeatedly? The answer may lie in how heat is distributed within Io's mantle. Tidal flexing doesn't occur evenly. It's strongest near the equator and weaker near the poles. This uneven heating could create zones of focused upwelling where magma breaks through more easily. Observations also suggest that Io's volcanoes may influence each other. Pressure changes in one region could trigger eruptions in another, forming a connected system rather than isolated vents. Earth-based telescopes play an important role in tracking these changes. Observatories equipped with adaptive optics can detect new eruptions almost as soon as they occur. Astronomers watch for bright infrared flashes, signals of molten lava breaking through the surface. These events often coincide with gravitational alignments or changes in Io's orbit, reinforcing the link between tidal stress and volcanic outbursts. Each eruption becomes a real-time experiment in planetary heating, allowing researchers to measure how quickly energy moves from the Moon's orbit into its crust and mantle. Even with all its violence, Io isn't entirely without structure or rhythm. Over time, scientists have noticed that many volcanic regions tend to reactivate in cycles. The surface at Loki Patera, for example, brightens and dims roughly every 500 days, consistent with waves of overturning magma. It's as if the lava lake breathes, molten rock sinking, cooling and rising again in a slow, deliberate heartbeat. On distant exoplanets orbiting close to their stars, tidal heating could drive volcanic worlds far larger than Io. Such planets might glow faintly in infrared light, detectable from across the galaxy. Io serves as a natural test case where the physics of gravitational heating can be observed directly. By measuring its eruptions, scientists refine their models of how energy moves through planetary interiors and how such energy might sustain activity or even habitability in other worlds. Dragonfly to Titan, science goals related to surface chemistry and habitability. Dragonfly represents a completely new kind of planetary mission. Titan's gravity is only about 1/7 that of Earth's, and its atmosphere is 4 times denser. Those conditions make flight not only possible but efficient. A single set of carbon fiber rotors can lift the entire vehicle easily, allowing it to travel kilometers at a time between landing sites. Each flight will be pre-programmed, chosen based on orbital data from Cassini, and refined with real-time readings from Dragonfly's own cameras and sensors. It will glide low through the hazy air, land softly, analyze the ground, and then lift off again. An explorer that can revisit its own discoveries, adapt to terrain, and chase new questions as they arise. The mission's main focus is chemistry. Cassini's instruments detected hydrocarbons and nitrogen compounds in its atmosphere, along with hints of heavier organics drifting down to the surface. Over time, that chemistry could have built up large, complex molecules, similar to those that once formed in Earth's primordial soup. Dragonfly's instruments are designed to investigate exactly that, to find out how far nature can go toward life without actually crossing the line into biology. At the heart of Dragonfly's science package is a mass spectrometer, a tool capable of identifying individual molecules by their atomic signatures. With it, scientists will examine the composition of Titan's surface materials and atmosphere, searching for amino acids, nitriles, and other building blocks of life. Another instrument will drill small samples into a miniature oven, heating them to release gases that can be analyzed for organic complexity. This combination of direct sampling and high-precision analysis will allow the team to piece together Titan's chemical story, how its organics formed, how they evolved, and whether any processes there resemble those that led to life on Earth. The choice of landing site is deliberate. Dragonfly will begin its mission in a region called Shangri-La, a vast dune field made of dark, organic-rich sands. These dunes are thought to be formed from particles that drift down from the upper atmosphere, then sculpted by Titan's winds. It's a place where surface materials and atmospheric chemistry meet, a perfect laboratory for studying how organic matter behaves under alien conditions. From there, Dragonfly will make its way toward an ancient impact crater known as Selk. The crater floor is believed to contain materials altered by heat and possibly mixed with subsurface water ice during the impact. Such regions may have once created warm, wet microenvironments, temporary oases where chemistry could have taken steps toward life. Dragonfly's cameras will give scientists their first close-up look at Titan's surface diversity. Cassini could only see vague shapes through the haze, but now individual rocks, dunes, and frost-covered plains will come into view. The vehicle will record panoramic images and stereo terrain maps, building a detailed picture of Titan's geology. Every flight will add to that picture, showing how the surface changes across different regions, how dunes fade into plains, how erosion shapes ridges, and how seasonal methane rainfall might leave patterns of deposits. Titan's geology is frozen in slow motion, moving on timescales far longer than Earth's, yet the processes are strikingly familiar. Beyond chemistry and geology, Dragonfly will study Titan's atmosphere in exquisite detail. Its sensors will measure temperature, pressure, wind speed, and methane humidity at different altitudes. It will monitor how the atmosphere interacts with the surface, how clouds form, how rain falls, and how organic haze particles settle. These measurements will help refine models of Titan's weather cycle. Understanding that cycle would yield new insights into how climates operate on worlds very different from our own. Powering such a machine on Titan requires ingenuity. Sunlight there is barely 1% as strong as it is on Earth, far too weak for solar panels to sustain flight or heating. Instead, Dragonfly uses a radioisotope thermoelectric generator, a small nuclear power source that converts heat from decaying plutonium into electricity. The same type of generator has powered spacecraft like Voyager, Cassini, and Curiosity for decades. On Titan, it will keep Dragonfly's instruments warm during the long nights, charge its batteries, and provide steady power for its sensors. This continuous energy source allows the mission to last for years, hopping from one site to the next at its own pace. Communication with Earth will be slow. Titan is more than 1 billion kilometers away, and radio signals take over an hour to cross the distance one way. Dragonfly will therefore operate autonomously for long periods, making decisions about flight and landing safety on its own. Each time it completes a flight and collects data, it will transmit summaries back to Earth for analysis. Scientists will study the results, decide the next set of targets, and send instructions during the next communication window. This rhythm, fly, sample, analyze, report, will repeat over and over, gradually mapping Titan's chemistry across multiple environments. One of the biggest questions the mission hopes to answer is whether Titan's chemistry is truly prebiotic. On Earth, before life emerged, simple molecules gradually assembled into more complex structures through cycles of reaction and concentration, perhaps in ponds, tides, or volcanic pools. On Titan, similar reactions might be occurring now. Lab experiments on Earth have shown that Titan's conditions could allow certain polymers to form spontaneously, including compounds that behave in vaguely cell-like ways, able to enclose material and maintain chemical gradients. If Dragonfly finds evidence of such compounds, it would suggest that nature can explore the boundary between non-life and life, even in environments utterly unlike Earth. Another intriguing aspect is Titan's possible subsurface ocean. If Dragonfly finds any hints of salts or ocean-derived compounds mixed into the surface organics, it could mean that Titan's chemistry is not isolated, that ingredients from a watery interior are interacting with the organic-rich exterior. Such exchanges could make Titan an even more promising location for studying life's potential. Dragonfly's findings will also have profound implications for how future missions are designed. If a rotorcraft can successfully navigate Titan's thick atmosphere and complex terrain, it opens the door to similar missions elsewhere. Planets and moons, once considered too challenging for surface exploration, could become reachable with flight-based vehicles. Even worlds like Venus or Triton might one day be explored with specialized drones adapted for their environments. Titan, in this sense, is a test case for a new generation of mobile exploration. Machines that can traverse diverse landscapes instead of being limited to a single landing site. As Dragonfly travels across Titan's surface, each landing site will reveal a different chapter. Dunes made of carbon-rich sand, plains dusted with chemical snow, craters filled with frozen residue from ancient impacts. Somewhere within those strange materials lies a record of chemistry that has been unfolding for billions of years, untouched by biology, yet tantalizingly close to it. Through its instruments and movement, Dragonfly will help scientists look back in time to an era when the line between organic chemistry and biology was thin and uncertain, and in that frozen haze, illuminated only by the faint light of a distant sun, we may find echoes of our own beginnings. Magnetospheric interactions, how Jupiter's field affects Europa, Ganymede, and Io. At its heart, Jupiter's magnetosphere is powered by the planet's own rotation. Unlike Earth's, which arises from the slow churning of molten iron in the core, Jupiter's field is generated by metallic hydrogen, a strange, compressed form of matter that behaves like a liquid metal deep inside the planet. As Jupiter spins once every 10 hours, this metallic layer whirls with incredible speed, generating a magnetic field so intense it dwarfs all others in the solar system. The result is a magnetic bubble that stretches several million kilometers toward the Sun and extends far beyond Saturn's orbit on the night side. Within this immense structure, space is anything but empty. Charged particles from the solar wind are trapped and accelerated within Jupiter's magnetosphere, creating radiation belts far stronger than those around Earth. In addition, material from Io, particularly sulfur and oxygen ions, feeds directly into this environment, forming a dense plasma torus that circles the planet. The interactions between Jupiter's field and this cloud of charged gas give rise to electrical currents that flow along magnetic field lines, linking the planet to its moons like invisible power cables. Each moon moves through this magnetic ocean differently, experiencing its effects in unique ways. Io, the innermost of the Galilean moons, endures the most extreme conditions. It orbits deep within Jupiter's radiation belts, where charged particles strike its surface continuously, stripping away atoms and molecules. But Io also fights back. Its hundreds of active volcanoes spew vast amounts of sulfur dioxide into space, which becomes ionized and swept up by the magnetic field. This process creates a constant exchange of material between the two magnetospheres, forming what scientists call the Io plasma torus. It's a glowing, donut-shaped band of charged particles that encircles the planet, emitting radio waves and ultraviolet light detectable from Earth. The magnetic connection between Io and Jupiter is so powerful that it generates a massive electric current, up to 5 million amperes, flowing along magnetic field lines between them. As this current slams into Jupiter's upper atmosphere, it creates brilliant auroras near the planet's poles. These Io-induced auroras are among the brightest in the solar system, a cosmic signature of the electrical tether binding Moon and planet together. Every time Io moves through Jupiter's field, it acts like a generator, converting orbital motion into electric energy. This continuous electrical interaction even affects Io's volcanic activity, as electromagnetic heating within its interior may add to the tidal forces already kneading the Moon's surface. Further out, Europa occupies a slightly calmer region, though still deep within Jupiter's magnetic grasp. The radiation environment here remains intense, thousands of times stronger than the radiation belt surrounding Earth, and it constantly bombards Europa's icy surface. When these high-energy particles collide with the ice, they split apart water molecules, producing oxygen and hydrogen. Some of the oxygen becomes trapped in the ice, while the rest forms a tenuous atmosphere around the Moon. This radiolysis continuously modifies the chemistry of Europa's surface, creating oxidants that could later mix into the subsurface ocean through cracks or convection. As Jupiter's magnetic field sweeps past the Moon, it induces electrical currents within Europa itself. These currents arise because of Europa's salty ocean, which is electrically conductive. When the external magnetic field changes direction, as it does while Jupiter rotates, it causes varying magnetic forces inside the Moon. By measuring these magnetic fluctuations, scientists can infer the presence, depth, and conductivity of Europa's hidden ocean. This magnetic induction technique has become one of the most powerful tools for exploring ocean worlds without the need to physically drill through the ice. As Juno flies repeatedly through Jupiter's magnetic environment, it measures how field lines bend and twist in response to the presence of its moons. These small distortions carry immense information. They reveal not only the structure of the moons, but also the flow of energy within the Jovian system. Each pass helps scientists map how Jupiter's magnetosphere interacts with its satellites, from the electric currents linking Io to the induction signals hidden beneath Europa's crust. When Ganymede, which has its own magnetic field, interacts with Jupiter's magnetosphere, complex boundaries form, creating auroras around Ganymede's poles. These auroras have been observed shifting slightly back and forth as Jupiter's magnetic field sweeps through. By analyzing those movements, scientists can measure how Ganymede's internal field responds, revealing details about the Moon's composition. When Hubble observed subtle oscillations in Ganymede's auroral ovals, researchers realized that the behavior could only be explained if an electrically conductive layer existed beneath its icy crust. In this way, magnetospheric science became a kind of remote X-ray for moons, invisible fields revealing the secrets of their interiors. Across all these moons, radiation and magnetism not only shape the environment, but also drive continuous chemical and physical changes. On Europa, the bombardment of charged particles can create sulfur and peroxide compounds, coloring parts of its surface and influencing its chemistry. On Ganymede, the interactions between the two magnetic fields may generate localized heating or even weak electrical currents within the ice. On Io, the flow of charged gas and plasma constantly replenishes Jupiter's magnetosphere itself, feeding the system with fresh energy. It's a symbiotic network, each moon contributing to and being sculpted by the same immense magnetic engine. For spacecraft, the radiation Jupiter's magnetosphere generates is a deadly hazard. The charged particles can damage electronics, erode surfaces, and interfere with instruments. Engineers designing missions must carefully plan trajectories and shielding to survive the intense bombardment. Yet the very radiation that poses such challenges is also what makes these moons so intriguing. It provides the energy to alter their surfaces, drive chemistry, and possibly sustain prebiotic processes in their hidden oceans. In many ways, Jupiter acts as both a destroyer and a creator. Its magnetic field tears molecules apart on the surfaces of its moons, but it also provides the electrical and chemical energy that could make life possible beneath them. The same radiation that sterilizes Europa's surface may also be delivering oxygen and other oxidants to its subsurface waters. The same electric currents that scorch Io's upper layers may also be fueling volcanic activity that keeps its core molten. Jupiter's magnetosphere, therefore, is the beating heart of an interconnected system, distributing energy across space in ways that blur the line between planet and satellite. Seen from this perspective, the Galilean moons are not isolated bodies orbiting a distant giant. They are participants in a shared environment, linked by invisible magnetic threads that pulse with energy and motion. Within this magnetic symphony, Europa, Ganymede, and Io are not passive spectators, but instruments, each resonating in its own way to the deep, unseen music of Jupiter's magnetic field. Heat sources in small moons, tidal flexing versus radiogenic heating in moons like Mimas. For decades, Mimas was dismissed as one of the solar system's least interesting worlds. Barely 400 kilometers across and pockmarked with craters, it looked like little more than a frozen relic. Cassini's images reinforced this impression, a dull, cratered sphere, with the enormous Herschel crater giving it the appearance of a Death Star. Yet beneath that quiet surface, there may be something stirring. Subtle variations in the moon's orbit and shape have led scientists to reconsider what lies inside. Against all expectations, Mimas might not be entirely frozen. It could be hiding a small internal ocean, maintained by heat generated from tidal flexing, an astonishing possibility for a moon once thought to be little more than a lump of ice and rock. At the heart of this new understanding is a simple question. How can such a small moon stay warm enough to keep liquid water beneath its crust? Normally, the smaller a body is, the faster it cools. With little internal mass to trap heat, small moons like Mimas should have frozen solid billions of years ago. Radiogenic heating, energy produced by the decay of radioactive elements such as uranium, thorium, and potassium, is a key heat source for many larger worlds. On Earth, it contributes significantly to the planet's internal warmth and drives plate tectonics and volcanic activity. But Mimas is far too small to sustain much radiogenic heat. Its limited rocky core would have exhausted that energy long ago, leaving no clear explanation for why it might still be active. And yet, when Cassini measured the moon's rotation and orbit, the data didn't quite add up. What Cassini found were slight oscillations or librations in the way Mimas wobbled as it orbited Saturn. These movements hinted that the moon's interior might not be completely solid. Instead, there could be a liquid layer deep below the ice shell, an ocean trapped beneath kilometers of frozen crust. Scientists had long thought Mimas was too small and too cold for any internal liquid water to survive. Yet the data left few alternatives. The pattern of librations could be explained either by a highly elongated core, which seemed physically unlikely, or by a hidden ocean that allowed the outer shell to move slightly independently of the interior. Mimas orbits very close to Saturn, just outside the planet's rings, where the gravitational forces are extreme. As it moves along its slightly elliptical orbit, the pull of Saturn's gravity changes subtly from one moment to the next. When Mimas is closer to Saturn, it is stretched. When it moves farther away, it relaxes. This heat produced by tidal flexing is perhaps just strong enough to keep a small portion of its interior from freezing completely. By simulating how Mimas's orbit and shape evolve over time, researchers can estimate how much tidal heat is produced inside it. The results suggest that, under certain orbital conditions, Enough heat could build up to melt a thin layer of ice deep below the surface, forming a buried ocean, perhaps a few tens of kilometers thick. This ocean would not be large or dynamic like those of Europa or Enceladus. It might be more like a slushy reservoir of liquid trapped between solid ice layers. But even that would be an extraordinary discovery for such a small world. Unlike Enceladus, which displays clear signs of activity, Mimas shows no obvious evidence of resurfacing. Its cratered landscape looks ancient, unchanged for billions of years. Could a moon really have an active ocean beneath such a static exterior? Some scientists suggest that Mimas may be in a transitional state, with its ocean recently formed or beginning to freeze. If the tidal heating rate changes slightly as the orbit evolves, the internal liquid could appear or disappear over time. In that case, Mimas might represent a snapshot of a phase that many icy moons go through, a temporary period of warmth before freezing permanently. If Mimas, one of the least geologically active bodies we know, can hide a subsurface ocean, then perhaps the threshold for internal activity is much lower than once believed. Moons once dismissed as frozen relics could, under the right conditions, harbor warmth and liquid water inside. It would mean that tidal heating is far more efficient than previously thought, capable of producing significant internal energy even in small, dense bodies. The outer solar system might therefore be teeming with hidden ocean worlds. The balance between tidal and radiogenic heating is delicate. Radiogenic decay provides a slow, steady supply of heat that diminishes over billions of years. It depends on the amount of radioactive material a body formed with, which in turn depends on its composition and origin. Tidal heating, by contrast, can fluctuate dramatically, changing as orbits evolve or as gravitational interactions with neighboring moons shift. In systems like Saturn's, these orbital resonances can maintain the eccentric orbits needed to sustain tidal heating over long timescales. For Mimas, the exact balance of these forces may be what determines whether its ocean remains liquid or eventually freezes solid. If its orbit changes slightly, tidal heating could decrease, allowing the interior to cool. Conversely, if the orbit becomes more eccentric, the stress could increase, briefly warming the interior again. While Mimas itself may not be a primary target of upcoming missions, the techniques developed for studying moons like Europa and Enceladus could eventually be applied to it. A single close flyby or a high-precision radar sounding might be enough to confirm whether a subsurface ocean truly exists. Similar processes might occur around other gas giants, both in our solar system and in exoplanetary systems. Many exoplanets likely host families of small moons, and some of those moons might be heated through tidal interactions just as Mimas is. In the outer solar system, where sunlight provides almost no warmth, the real engines of activity lie within. Beneath the cold silence of Mimas and moons like it, there may still be motion that defies the darkness of space. New surface chemistry on Triton. When Voyager 2 flew past Neptune in 1989, it captured plumes of dark material rising miles above the surface of Triton, drifting across the landscape and leaving streaks hundreds of kilometers long. More than 3 decades later, modern observations are finally beginning to reveal just how active this distant world remains. Telescopes like Hubble and ground-based observatories equipped with infrared spectrometers have provided glimpses of Triton's changing face. By studying how sunlight reflects off the surface and how different wavelengths are absorbed, scientists can detect the chemical fingerprints of materials that coat it. These observations show fresh nitrogen frost covering large regions, suggesting that the ice layer is not ancient but continuously renewed. In some areas, deposits of carbon monoxide and carbon dioxide appear and fade over time, a sign of subtle but ongoing seasonal cycles. Triton, it seems, is not a static relic, but a living, shifting environment, one that defies expectations for a body so far from the warmth of the sun. The reason this discovery is so important lies in how these changes happen. Triton's surface temperature hovers around -235 degrees Celsius, cold enough that most chemical reactions slow to near standstill. Yet something is clearly driving movement and renewal. Scientists suspect that sunlight, weak as it is at Neptune's distance, may still play a key role. When the faint rays strike dark patches of the surface, they can warm small regions of nitrogen ice just enough to turn it into gas. This trapped gas builds up pressure under the surface until it bursts through, creating geysers that spray fine particles of ice and dust into the thin atmosphere. Once airborne, these materials settle elsewhere, forming bright new frost or thin coatings of different chemicals. Over decades, this process could reshape Triton's appearance, a form of weather operating in slow motion, guided by sunlight billions of kilometers from home. Observations from the Gemini North Telescope in Hawaii have confirmed variations in the spectral signatures of nitrogen and carbon monoxide frost across the surface. These changes are thought to be linked to Triton's highly tilted and eccentric orbit, which gives it extreme seasonal variations. Unlike Earth, where seasons last a few months, Tritons can span decades. During these long cycles, entire hemispheres are alternately bathed in sunlight or cast into darkness. The difference in heating, though minimal, could be enough to shift gases and ices from one pole to another. Over time, this migration of material creates new layers and removes old ones. Triton is widely believed to be a captured Kuiper belt object, a distant cousin of Pluto that wandered too close to Neptune and was caught by its gravity. This capture would have generated immense tidal forces as Triton's orbit settled, producing intense internal heat. Though much of that energy has long since dissipated, some of it may still linger deep inside. If so, it could provide an additional heat source, keeping parts of the subsurface active and capable of driving geysers from below. Hubble's observations support this view. Images taken years apart show subtle changes in brightness patterns across Triton's surface, a clue that frost is redistributing itself. In some regions, bright nitrogen deposits fade, replaced by darker patches that suggest the exposure of older or more volatile materials. The appearance of carbon monoxide frost in particular has drawn attention. Carbon monoxide behaves differently from nitrogen. It sublimates and condenses under slightly different conditions, meaning it can separate from nitrogen ice and form its own seasonal layers. This separation could be evidence of fractionation, a process where volatile ices sort themselves based on how easily they evaporate. Such fractionation has been observed on Pluto as well, suggesting that similar chemistry might occur across many outer solar system worlds. What fascinates researchers is that these surface changes might not just be superficial. If Triton's geysers still erupt from beneath, they could be connected to deeper layers of volatile material, possibly even reservoirs of liquid or slushy nitrogen beneath the crust. Some models propose that sunlight warms the subsurface through translucent layers of ice, allowing pockets of gas to accumulate and vent periodically. The fine particles ejected during these eruptions then drift in Triton's tenuous atmosphere before settling back down. Over time, this creates a feedback system where sunlight drives frost migration, geysers redistribute material, and new frost layers form. While Triton's orbital period around Neptune is just under 6 days, its year, the time it takes to orbit the Sun, lasts 165 Earth years. As seasons progress, the pole facing the Sun changes slowly, altering which regions receive light. Studies suggest that during these shifts, the balance of frost types on the surface can change measurably within just a few decades. That's remarkably fast on a geological scale, hinting at a surface in motion even in the coldest reaches of the solar system. When ultraviolet light from the distant Sun hits these ices, it can trigger photochemical reactions, creating new compounds that accumulate over time. Some of these reactions could produce complex organic molecules, the same kind that have been detected on Pluto and other trans-Neptunian objects. In this sense, Triton could be not just geologically active, but chemically creative as well. NASA has considered concepts like Trident, a flyby mission proposed to visit Triton and map its surface chemistry, magnetic environment, and potential plumes. If launched, it would provide the first close-up view of the Moon, in more than half a century. By comparing new imagery with Voyager's, scientists could directly observe how much the surface has changed and identify active regions. Instruments capable of detecting trace gases and surface compositions could reveal whether Triton still vents material into space. Beneath its pastel-colored frost plains and beneath its whisper-thin atmosphere, there are processes unfolding on timescales too slow for the human eye, but unmistakable in the record of light reflected back through telescopes. Triton, once thought to be just another frozen relic, is turning out to be a world where even the coldest materials dance to the rhythm of energy and time. Dark material on Iapetus and Phoebe. Iapetus, the third largest moon of Saturn, has one hemisphere that gleams brightly in sunlight, almost as reflective as snow, while the other appears as dark as asphalt. The line between them is abrupt, not gradual, a literal division between light and shadow. This mysterious dichotomy has puzzled astronomers since the 1600s, when Giovanni Cassini, for whom the spacecraft was later named, first noticed that Iapetus's brightness seemed to change depending on its position in the sky. Centuries later, with high-resolution images and spectral data, scientists finally began to piece together the story of what creates this strange two-toned world. At first glance, Iapetus seems like two moons fused together. The leading hemisphere, known as Cassini Regio, is coated in a dark, reddish-brown material that absorbs sunlight efficiently. The trailing hemisphere, on the other hand, is covered in bright ice, reflecting nearly all the light that strikes it. This sharp contrast would be unusual for any planetary body, but especially for one orbiting so far from the Sun, where temperature differences should be mild and processes slow. Yet the data from Cassini's Visual and Infrared Mapping Spectrometer, or VIMS, revealed that something more complex was happening, a dynamic interplay between external dust, solar radiation, and internal feedback mechanisms that reshaped Iapetus over millions of years. The key to the mystery lies with another moon, Phoebe, a small, dark, irregularly shaped body that orbits Saturn much farther out than Iapetus. Phoebe's surface is coated with carbon-rich compounds, likely remnants from the early solar system. These materials absorb heat well and have the same kind of spectral fingerprints as the dark coating found on Iapetus. Cassini's data suggested that micrometeoroid impacts on Phoebe constantly eject fine dust into space. Over time, this material drifts inward towards Saturn, forming a vast faint ring known as the Phoebe ring. As Iapetus moves through this ring, it collects the drifting particles, which gradually settle onto its leading hemisphere, the side that faces forward in its orbit, like a car's windshield catching bugs. This slow dustfall would have started an intriguing chain reaction. As dark particles accumulated, they caused the surface to absorb more sunlight. That extra warmth, though still weak compared to Earth's, was enough to make a difference. The icy surface beneath began to sublimate, turning directly from solid to gas, and migrate toward cooler regions. Over time, the bright ice evaporated from the darkened areas and recondensed on the colder, brighter side, reinforcing the contrast. This process, known as thermal segregation, acts like a self-perpetuating engine. Once started, it keeps amplifying the differences, until the moon ends up with one hemisphere almost entirely dark and the other pristine white. Cassini's observations confirmed that the boundary between the two hemispheres isn't simply a coating of soot. Instead, it's a complex transition zone where dark material mixes with bright ice. The deposits are shallow, only a few centimeters thick in some areas, but their effect on surface temperature is dramatic. In regions where the coating is dense, the surface can be tens of degrees warmer than the neighboring icy plains. This temperature difference further drives the sublimation of ice, which migrates and settles on cooler slopes. The process resembles a slow-motion erosion, except it's caused not by water or wind, but by sunlight and chemistry. Scientists found evidence that the dark material coating Iapetus isn't purely carbon dust either. Cassini's infrared spectrometer detected traces of complex organic compounds, possibly tholins, which are reddish polymers created when simple molecules like methane and nitrogen are exposed to ultraviolet light. Tholins are thought to form naturally in the outer solar system and could be widespread on moons, comets, and asteroids. Their presence on Iapetus suggests that the dust from Phoebe has been chemically altered by radiation during its long journey inward. When this material lands on Iapetus, it mixes with local ice, creating a mosaic of color and composition across the surface. Both moons share a similar inclination in their orbits and show related spectral features. Phoebe itself appears to be an ancient interloper, a captured object from the Kuiper belt. Its surface is old and cratered, covered with dark carbonaceous material rich in organics. The idea that material from such a body could migrate inward and modify another moon demonstrates how interconnected the Saturnian system truly is. Even at vast distances, slow but persistent processes can link distant worlds through dust and gravity. The Phoebe ring, though faint and invisible to the naked eye, provides a direct pathway for this exchange. Discovered in 2009 through infrared observations, the ring extends millions of kilometers from Saturn and is tilted relative to the planet's main rings. Its particles are thought to range from microscopic grains to chunks several centimeters wide, slowly spiraling inward under the influence of sunlight pressure and Saturn's gravity. As Iapetus orbits near the edge of this enormous ring, it becomes a natural collector, sweeping through the drifting debris like a slow-moving net. Over billions of years, this accumulation has completely altered its appearance. The transformation didn't require any violent geological event. No volcanism, no impacts, no massive eruptions, just dust and sunlight. Yet the outcome is striking enough to rival the most dramatic planetary landscapes. On a global scale, the process reveals how even subtle environmental differences can cascade into dramatic changes over geological time. In this case, a small variation in surface color led to changes in heat absorption, which in turn changed ice stability, which then reinforced the color difference again. A perfect example of positive feedback in nature. Traditionally, astronomers viewed moons like Iapetus as passive, their surfaces shaped only by impacts and the slow accumulation of ice. But the story of Iapetus shows that surface chemistry and radiation can create intricate and self-organizing patterns even in seemingly inert environments. Every moon, no matter how small, interacts with its environment, exchanging materials, light and energy in subtle but enduring ways. Cassini's close flyby of Phoebe revealed a surface covered in craters and streaked with material of varying brightness. The spacecraft detected signs of both water ice and dark organic compounds, suggesting that Phoebe might once have had internal heat and even limited water activity early in its history. Its density and composition make it very different from Saturn's other moons, reinforcing the theory that it came from much farther out in the solar system. The dark material coating its surface likely formed through a combination of ancient impacts and radiation chemistry, the same types of processes that might have once shaped the surfaces of comets and Kuiper belt objects. By studying Iapetus and Phoebe together, scientists gain insight into how dust and radiation can sculpt moons across the outer planets. Similar processes may be occurring around Jupiter and Uranus as well. Over time, slow migration of material could modify the appearance of other moons, producing patterns that encode the history of their surroundings. The dark hemisphere will continue to warm and shed volatile ices, while the bright side may grow even whiter as frost accumulates. Eventually, as dust deposition continues and Saturn's distant environment evolves, the balance could shift again. Hyperion's porosity and the role of micrometeoroid impacts. Hyperion is an object that seems to defy what a moon should look like. When Cassini first approached it in 2005, the spacecraft's cameras captured a surface that wasn't smooth or even rugged in the usual way. Instead, it appeared as if the entire moon had been carved from a cosmic sponge, riddled with craters upon craters, with deep pits and sharp ridges that cast dramatic shadows across its honeycomb-like terrain. To the naked eye, it seemed fragile, as though one hard nudge might break it apart. Scientists were immediately fascinated. How could such a delicate-looking world have survived for billions of years, orbiting within Saturn's immense gravitational field? The answer, as later research would show, lies in Hyperion's remarkable porosity, the fact that most of its interior is empty space. Estimates from Cassini's instruments suggest that about 40% of Hyperion's volume consists of voids. In other words, it is not a solid rock, but a loosely bound collection of icy rubble. This extreme porosity gives it an unusually low density, only about half that of water ice. If it were placed in a sufficiently large ocean, Hyperion would float. But its lightness comes with consequences. Its weak gravity, barely enough to hold itself together, prevents debris from settling and compacting. Every impact leaves a distinct mark, preserved almost exactly as it occurred, making its surface a record of the tiniest and most ancient collisions in Saturn's neighborhood. Cassini's close-up images showed that Hyperion's craters have unusually sharp edges and deep, narrow walls, unlike those on denser moons where gravity tends to pull debris down and soften the landscape. On Hyperion, when a meteorite strikes, the impact energy travels differently. Instead of spreading widely through the surface, it disperses through the porous material, absorbing much of the shock like a cushion. The ejected material often escapes into space rather than falling back, since the moon's gravity is too weak to hold it. Over time, this process leaves behind craters that look hollowed out and steep, giving the moon its characteristic spongy appearance. Micrometeoroid impacts, collisions with particles as small as grains of sand, play a key role in maintaining this strange texture. In the outer solar system, there's a constant rain of such debris, leftover material from comets, broken moons, and the slow grinding of dust rings. Hyperion, lacking a strong atmosphere or magnetic protection, takes the full brunt of this endless bombardment. Each tiny impact shakes loose bits of ice and rock without compressing them. Because there's so little gravity to pull the material back, the loosened debris either drifts away or settles gently back into the cavities, never fusing into a compact layer. Over billions of years, this steady drizzle of impacts has kept the moon's surface porous and rough, turning it into one of the most chaotic terrains in the solar system. Computer models developed after Cassini's mission support this explanation. Simulations show that Hyperion's low density allows craters to form differently than on solid worlds. When a small impactor strikes, it doesn't compress the target, but instead blows away loose particles, carving deep cavities with relatively little energy. Because the subsurface is filled with voids, the shockwave gets dampened rapidly, preventing large cracks from spreading. The end result is a surface that retains an irregular foam-like structure, built up layer by layer through countless minor collisions, rather than reshaped by a few major ones. The models also explain why Hyperion's craters seem to overlap without erasing each other. Each new impact simply punches another hole in the porous surface, leaving the surrounding structure mostly intact. If its composition were even slightly denser, it would compact under its own gravity, flattening its features over time. If it were lighter, it might not have survived at all. Its porosity gives it resilience against shattering, since the empty spaces inside act like shock absorbers. Instead of cracking apart, Hyperion gives when struck, dissipating energy through its open network of cavities. This quality could explain how it has survived countless impacts that might have destroyed a more rigid body. Cassini's instruments also detected a faint electrostatic environment surrounding Hyperion. When the spacecraft flew close by, it experienced a brief jolt of electrical charge, as if it had brushed through a cloud of charged particles. Scientists believe this was caused by sunlight knocking electrons off Hyperion's surface, which then interacted with Saturn's magnetosphere. The moon's irregular shape and low gravity mean these particles can easily escape, forming a temporary halo of static electricity. Unlike most moons, it doesn't have a stable day-night cycle. Its irregular shape and proximity to Titan cause it to tumble chaotically through space, spinning unpredictably rather than maintaining a consistent orientation. Cassini's long-distance observations showed that its rotation axis wobbles constantly, changing from one orbit to the next. This tumbling motion further affects how sunlight hits its surface, possibly influencing local temperature variations and the behavior of charged particles around it. It also means that over time, all parts of Hyperion are exposed to similar levels of sunlight and micrometeoroid bombardment, leading to a more uniform surface appearance than one might expect from a tidally locked moon. Spectral data revealed that Hyperion's surface is composed primarily of water ice mixed with small amounts of dark reddish material, likely organic compounds similar to those found on Iapetus and Phoebe. This dark dust may have originated from the same outer Saturnian sources, gradually coating Hyperion as it moved through the faint rings of debris. However, because of its porous surface, the material tends to collect unevenly, accentuating its already mottled appearance. Some of the dark compounds could also form locally when cosmic radiation interacts with simple ices, breaking apart molecules and triggering chemical reactions that produce more complex organic residues. Scientists think Hyperion may be a remnant from the early days of Saturn's system, when collisions between proto-moons created debris fields that later coalesced into irregular bodies. Unlike its larger neighbors, it never experienced enough internal heat to melt or differentiate. Instead, it remained a cold collection of ice and dust, preserving a snapshot of the conditions that existed more than 4 billion years ago. Because its density and composition are similar to those of comets, studying Hyperion can also shed light on how cometary nuclei survive repeated passages through the solar system. Both types of bodies share a porous structure and are shaped by continuous impacts. In this sense, Hyperion might represent a transitional object, not quite a moon in the traditional sense, yet no longer a comet either. It occupies a middle ground between the solid satellites of the giant planets and the fragile debris that drifts among them. How porous can a body be and still remain intact under gravity's pull? Theoretical studies suggest that Hyperion is near this boundary. Its internal strength is barely enough to prevent it from breaking apart. Yet it manages to maintain coherence thanks to the gentle balance between its mass, shape, and orbital forces. If another large object were to collide with it, the impact might scatter it completely, turning it into a temporary cluster of fragments orbiting Saturn. For now, however, it continues to drift quietly, spinning and tumbling, its sponge-like body absorbing the slow rain of micrometeoroids that have sculpted it since the dawn of the solar system. Mars's moons. Phobos and Deimos. Fresh clues from high-resolution surface mapping. Unlike the grand spherical moons of Jupiter or the dynamic ice worlds of Saturn, Mars's two small moons, Phobos and Deimos, seem humble and unassuming. Phobos, the larger of the two, orbits Mars so closely that it completes a revolution in just over 7 hours, faster than Mars rotates on its axis. To an observer on the Martian surface, Phobos would rise in the west and set in the east, racing across the sky 3 times each Martian day. That closeness, however, comes at a cost. Tidal forces from Mars are slowly pulling Phobos inward, lowering its orbit by about 2 centimeters per year. Over time, this gravitational tug is literally tearing the moon apart from within. The evidence of that stress might already be visible in the patterns that crisscross its surface. Long grooves, ridges, and shallow crater chains that form an eerie network over the moon's face. When the first close-up images from the Viking orbiters arrived in the 1970s, these grooves immediately puzzled scientists. Were they fractures caused by Mars's tides, the scars of ancient impacts, or the result of surface material sliding downhill following the moon's irregular gravity field? Decades later, with higher resolution data from Mars Express and the Mars Reconnaissance Orbiter, researchers began to piece together a more complex story. Many of the grooves aligned toward the massive impact crater known as Stickney, suggesting they might have formed as ejector patterns or as fractures radiating outward from that colossal collision. But others do not line up at all. They curve around the moon's surface in ways that seem more consistent with internal stress than with a single explosive event. This has led to the theory that the grooves on Phobos are not just scars of the past, but signs of a moon actively being torn apart. As tidal forces flex Phobos' interior, they may be causing its outer layers to crack, producing new surface features over time. Some computer simulations suggest that the Moon is slowly transforming into a loose pile of rubble held together by weak gravity, and that within 30 to 50 million years, it could break apart entirely, forming a temporary ring around Mars. The grooves, in this interpretation, are like stretch marks on a doomed body, visual evidence of a slow-motion disintegration. Deimos, orbiting farther out, tells a very different story. It circles Mars in a nearly circular equatorial orbit, moving slowly and serenely, taking about 30 hours to complete one revolution. Where Phobos is heavily grooved and misshapen, Deimos is smoother, more symmetrical and less scarred by impacts. Yet even here, the surface is not as simple as it appears. Subtle signs of regolith migration, fine dust and small grains shifting across the terrain, suggest that even in the low-gravity environment, forces like solar radiation, micrometeorite impacts, and perhaps seismic shaking from distant collisions are reshaping its surface layer by layer. Deimos's craters are shallower than expected, implying that its surface may be covered with a deep layer of fine material that fills in older features, creating the smoother look that distinguishes it from its sibling. High-resolution mapping from instruments aboard Mars Express and India's Mars Orbiter mission has revealed details that were previously invisible. Scientists have used these data to model how each moon reflects light, how its composition varies from place to place, and how temperature changes over the Martian day-night cycle. On Phobos, dark patches enriched with carbon-rich compounds hint at a primitive composition, something more akin to a captured asteroid than to a piece of Mars itself. Deimos too reflects light in a way that matches certain classes of carbonaceous asteroids found in the outer belt, suggesting that both moons might have originated from material that formed far from Mars and was later captured by its gravity. But this asteroid capture theory has long faced a problem. If Phobos and Deimos were truly captured objects, their orbits should be more elliptical and inclined, reflecting the chaotic process of capture. Instead, both moons orbit almost exactly in Mars's equatorial plane and in nearly circular paths, more like moons that formed around the planet itself. This contradiction has kept scientists divided for decades. Some models suggest that Mars once had a much larger moon that broke apart after a massive impact, scattering debris that later coalesced into the two smaller bodies we see today. Others argue that gas and dust around Mars in its early history might have slowed down passing asteroids, allowing them to settle into stable circular orbits. Each hypothesis has strengths and weaknesses, and none has yet managed to explain all the evidence. That's where Japan's upcoming MMX mission, Martian Moons Exploration, comes in. Scheduled for launch later this decade, MMX will attempt something no mission has ever done: land on Phobos, collect samples, and bring them back to Earth. Equipped with a suite of cameras, spectrometers, and dust analyzers, the spacecraft will study both moons in detail before descending to Phobos' surface. Once there, it will use a small robotic arm to scoop up material, potentially collecting grains that have been untouched for billions of years. When those samples are returned, scientists will be able to analyze their isotopic ratios and mineral content with precision impossible from orbit. If Phobos' material matches that of certain asteroid types, the capture theory will gain strong support. If instead it shares chemistry with the Martian crust, that would point to an origin from a massive impact early in Mars's history. Phobos' regolith appears to be composed of extremely fine, fluffy particles that behave differently from lunar soil. When disturbed, these grains seem to move more easily, as if electrostatic forces and microgravity create a fluid-like effect. In certain regions, the soil forms streaks and flows that align with local topography, possibly driven by even small seismic vibrations. The faint rings of ejecta around some craters suggest that impacts on Phobos loft material into temporary orbits before it settles back, creating layers upon layers of dust that could record the moon's environmental history like pages in a book. The Stickney crater itself is a reminder of how fragile the moon truly is, Measuring about 9 kilometers across, almost half the diameter of Phobos, it's astonishing that such an impact didn't destroy the Moon entirely. Numerical models suggest that the collision that formed Stickney may have sent shockwaves through the entire body, shaking loose material and possibly altering its internal structure. The faint grooves that stretch outward from the crater could be the surface echoes of that ancient cataclysm, preserved through billions of years of slow evolution. Deimos, while less dramatic, presents its own mysteries. Some of its features indicate resurfacing events that might have buried older craters. There are also hints of a past interaction with ring material or dust clouds generated by Phobos's gradual erosion. The relationship between the two moons might be more dynamic than once thought. Some scientists speculate that dust escaping from Phobos could migrate outward and settle on Deimos over long timescales, creating subtle compositional gradients. The MMX mission will also deploy a small rover, jointly developed with the German and French space agencies, to explore Phobos's surface up close. This rover will test how mobility works in ultra-low gravity and provide a human perspective on an environment where even a gentle push could send an object drifting away. By studying how dust, rocks, and mechanical systems behave there, engineers hope to gain insight into how future missions might operate in similar environments, whether around small moons, asteroids, or even artificial satellites. Through these upcoming missions and ongoing analyses, Phobos and Deimos are slowly being transformed from distant, grainy shapes into detailed worlds with complex stories. What they reveal about Mars's past, and possibly about the broader history of the inner solar system, will depend on how deeply we can read those marks, the grooves, ridges, and quiet plains that tell of billions of years of motion, collision, and transformation. The possibility of briny water layers on Ceres. Ceres, the largest object in the asteroid belt, sits between Mars and Jupiter in a region of the solar system that is neither quite rocky nor entirely icy. At first glance, it looks like a grey, cratered world, an unremarkable relic of planetary formation. But the closer the Dawn spacecraft drew to it, the more it became clear that Ceres was anything but ordinary. Beneath its cold and dusty surface, scientists found signs of salt, chemistry, and possibly even liquid water. It blurred the line between asteroid and moon, showing behaviors more reminiscent of icy worlds like Europa or Enceladus than the lifeless rocks that surround it. When Dawn entered orbit around Ceres in 2015, it became the first spacecraft to ever orbit a dwarf planet. Its mission was to map Ceres' surface, measure its mineral composition, and study its internal structure. Almost immediately, it discovered bright spots inside several craters, reflecting sunlight far more strongly than the surrounding dark terrain. At first, they seemed like ice, but further analysis revealed that they were made primarily of sodium carbonate, a type of salt. This was a surprise because such materials typically form when liquid water evaporates, leaving behind mineral residues. The implication was that somewhere in Ceres' history, and possibly even today, water had been present as a liquid. The most famous of these bright regions lies in Okator crater, a 92-kilometer-wide depression. At its center lies a brilliant dome-like feature surrounded by radiating fractures, a structure that looks more like a frozen spring than an impact scar. Dawn's instruments detected hydrated salts and carbonates there, indicating that briny liquids had once seeped upward from below the surface and crystallized as they reached the vacuum of space. These deposits appear geologically young, no more than a few million years old, suggesting that the processes that formed them may still be ongoing in some form. For a world just 940 kilometers across, that was astonishing. Gravity measurements taken by Dawn suggest that Ceres isn't a solid rock throughout. Instead, it has differentiated into layers, a rocky core, an icy mantle, and a crust laced with salts and clays. The ice layer, although mostly frozen, might contain patches where salts and ammonia lower the freezing point of water, allowing it to remain liquid at temperatures well below zero. These briny pockets could persist for long periods, trapped between layers of ice and rock. One of the mysteries of Ceres is how it maintains these possible liquid layers despite its small size and distance from the Sun. Unlike Europa or Enceladus, Ceres has no giant planet nearby to provide tidal heating. Instead, its internal warmth likely comes from the decay of radioactive elements in its rocky core, uranium, thorium, and potassium, producing just enough energy to keep parts of the mantle warm. When mixed with salts and volatile compounds like ammonia, even a little heat can maintain pockets of brine. Over time, these liquids might migrate toward the surface through cracks or impact fractures, emerging briefly before freezing again. It's a slow, cyclical process, a hidden plumbing system operating just beneath the crust of a dwarf planet. Dawn's infrared spectrometer also detected materials that hint at ongoing chemistry. Ammonium-bearing clays, for example, suggest interactions between rock and liquid that could alter the surface composition. These clays are not easily produced by dry processes. They typically require the presence of water at some stage. The discovery of carbonates further strengthens the idea that Ceres once had an environment rich in carbon and hydrogen, ingredients essential for prebiotic chemistry. Interestingly, Ceres also shows signs of transient activity. Dawn's instruments recorded localized hazes, thin, temporary clouds of water vapor that seem to appear during certain times of the day. These hazes might form when sunlight warms salty patches of the surface, causing sublimation. Alternatively, they could be remnants of deeper outgassing events, where briny water briefly reaches the surface and releases vapor before freezing over again. The chemical environment on Ceres resembles, in miniature, the conditions thought to exist on much larger ocean worlds. Ceres, smaller and colder, may host a patchwork of briny regions instead of a global sea, but the underlying chemistry could be similar. By studying Ceres, scientists can test models of how salts, ice, and rock behave under low gravity and low temperatures. Models that can then be applied to understanding the icy moons of the outer solar system, which are much further away and thus harder to study. The distribution of bright materials across Ceres also tells a story of dynamic resurfacing. Many bright patches are located along crater rims or slopes, places where impacts have exposed fresh material from below. Over time, these areas darken as space weathering alters the salts, but new impacts or cryovolcanic eruptions may renew them. In some cases, bright deposits appear to have formed from liquid that erupted onto the surface and froze in place. These cryovolcanic features are subtle, nothing like the towering plumes on Enceladus, but they suggest that internal pressure, perhaps from expanding brines or gas, can occasionally break through the crust. Ahuna Mons, a solitary mountain rising nearly 5 kilometers above the surrounding plain, may be the most dramatic evidence of this process. It resembles a cryovolcano, and its slopes are streaked with reflective deposits similar to those found in Okator crater, implying a shared origin. The age of Ahuna Mons is estimated at only a few 100 million years, meaning it is a recent feature on a geological timescale. That youthfulness reinforces the idea that Ceres's interior remains active enough to reshape its surface from time to time. The presence of carbonates, clays, and salts implies that water-rock interactions were common during that formative period. By analyzing the proportions of these minerals, scientists can reconstruct the chemical pathways that shaped not only Ceres but other primitive bodies. This information feeds into larger models of planetary formation, helping explain how volatile rich materials were distributed between the inner and outer solar system. With the Dawn spacecraft now silent, scientists rely on its archived data to make new discoveries. But proposals for follow-up missions, possibly including landers or drills, aim to directly sample the bright deposits and probe beneath the surface. Instruments capable of detecting trace gases or measuring electrical conductivity could confirm whether liquid water still exists underground. A radar sounder, for example, might reveal layers of ice, rock, and brine within the crust, painting a three-dimensional picture of Ceres's hidden structure. Detection of ammonia or ammonium salts on Kuiper belt moons. Far beyond Neptune, the solar system grows dim and slow. The Sun is no longer a blazing sphere in the sky, but a bright star surrounded by an endless sea of frozen worlds. These distant objects, known collectively as the Kuiper belt, were once thought to be the most static and ancient remnants of planetary formation. They were imagined as icy fossils, unchanged for billions of years. Yet, as modern telescopes and spacecraft have revealed, many of them are far more dynamic than expected. Among the most intriguing discoveries in recent years is the detection of ammonia and ammonium-bearing compounds on several Kuiper belt moons and dwarf planets. These chemicals have been found on bodies like Pluto's moon Charon, and possibly on smaller companions such as Nix and Hydra, as well as on other large Kuiper belt objects like Orcus and Quaoar. The presence of these nitrogen-rich compounds suggests that these icy bodies once harbored enough heat to allow for internal differentiation, liquid water, and even cryovolcanic activity. The key lies in the unique properties of ammonia. When mixed with water, ammonia acts as an antifreeze, which means that even in the frigid outer solar system, where surface temperatures plunge below -200 degrees Celsius, subsurface layers enriched with ammonia could have stayed fluid for millions or even billions of years. The first strong evidence for ammonia-bearing materials came from observations of Charon, Pluto's largest moon. Data from the New Horizons spacecraft, as well as ground-based infrared spectroscopy, showed distinct absorption features in the near-infrared spectrum, signatures of ammonia hydrates and ammonium salts. These were found in specific patches, especially around young craters and smooth plains, suggesting they were exposed by relatively recent geological activity. Over long timescales, ammonia should be destroyed by radiation from the Sun and cosmic rays, so its presence on the surface implies that it must have been replenished from below, possibly through cryovolcanic flows or sublimation-driven resurfacing. When New Horizons flew past Pluto and Charon in 2015, it provided an unprecedented look at this frozen system. Pluto itself showed signs of nitrogen ice flows, mountain ranges of water ice, and a thin but complex atmosphere. Charon, by contrast, revealed a landscape carved by immense chasms, smooth plains and fractures stretching for hundreds of kilometers. These features pointed toward past tectonic or cryovolcanic processes, evidence that the moon had once expanded as internal water froze and expanded, cracking its outer shell. The detection of ammonia-related compounds strengthened this interpretation. It indicated that liquid, or at least partially molten, layers once existed beneath the surface and may have carried these chemicals upward. Other Kuiper belt objects have shown similar spectral fingerprints. Orcus, often called a twin of Pluto due to its comparable size and composition, exhibits ammonia-bearing ices on its surface. Quaoar, another large object, also shows hints of ammonia and possibly methane hydrates. These detections come from infrared observations made by telescopes like Gemini North and the Very Large Telescope, which can distinguish subtle differences in light reflected off icy surfaces. The recurrence of ammonia among several distant objects suggests that it is not a rare contaminant, but a widespread component of outer solar system chemistry. It might have been built into these bodies from the beginning, mixed into the primordial ices that formed beyond Neptune's orbit. For a small body to retain liquid water for extended periods, it must have some source of internal heat. Radioactive decay within the core can provide this energy, and for larger Kuiper belt objects, gravitational compression and past collisions could also have generated temporary warmth. If ammonia was present in the original mixture, even modest heating would have been enough to melt some of the ice, creating slushy or briny interiors. As the body cooled, the liquid might have gradually refrozen, pushing ammonia-rich fluids toward the surface and creating patches of fresh material detectable today. Cryovolcanism becomes a natural outcome of this process. On worlds like Pluto or Charon, ammonia-rich brines could have seeped upward through fractures, freezing as they emerged and leaving behind bright, fresh deposits. Such activity could explain the smooth plains observed by New Horizons, where resurfacing appears to have erased ancient craters. Similar mechanisms may also be at work on other large trans-Neptunian objects, though they are too distant for direct imaging at present. Each new spectral detection of ammonia adds weight to the idea that the Kuiper belt is a region where chemical and geological evolution still occur, albeit at glacial speeds. On Earth, ammonia is a key component in the nitrogen cycle, essential to biological processes. In extraterrestrial environments, it serves a different but equally crucial role. It maintains liquid conditions and supports complex chemistry at extremely low temperatures. If subsurface oceans once existed, or still exist, beneath the crusts of these Kuiper belt moons, they would likely be enriched with ammonia, methane, and other volatiles. Within such environments, energy from radioactive decay or chemical gradients between rock and water could drive reactions similar to those thought to have occurred in the early oceans of Earth. Even if life never developed there, these ammonia-rich worlds preserve a record of prebiotic chemistry. Scientists believe that many of the building blocks for life, amino acids, organic molecules, and nitrates, could have formed in such environments and later been delivered to the inner planets via comets and meteorites. In that sense, the ammonia and ammonium salts found on Kuiper belt moons could represent chemical bridges between the earliest stages of planetary formation and the origins of life on Earth. Over millions of years, cosmic rays and solar particles bombard these icy surfaces, altering ammonia and other molecules through chemical reactions. Ammonia can be converted into ammonium salts or more complex organic residues, changing the reflectivity and color of the surface. The reddish and brownish hues seen on many Kuiper belt objects might partly result from such radiation-driven chemistry. By comparing spectral data from different moons, researchers can estimate how long a surface has been exposed or resurfaced. Areas with stronger ammonia signatures are likely younger, while darker, redder regions may have been weathered for eons. The James Webb Space Telescope, with its powerful infrared instruments, has already begun collecting detailed spectra from several Kuiper belt objects, far surpassing what ground-based telescopes could achieve. Early results hint at variations in ammonia distribution from one body to another, suggesting differences in composition or thermal history. As more data arrives, scientists hope to map the relationships between ammonia, methane, and water ice, an essential step toward reconstructing the geochemical evolution of the outer solar system. There is also growing interest in sending missions to explore these remote objects directly. While reaching the Kuiper belt poses enormous technical challenges, the success of New Horizons has shown that it is possible. A future flyby mission, equipped with modern instruments capable of detecting trace gases and mapping mineral compositions, could reveal whether ammonia-related materials are widespread beneath the surface or concentrated in isolated regions. Even limited sampling could tell us whether cryovolcanic activity still occurs today or if it ended long ago, leaving only frozen traces behind. The Kuiper belt, once seen as the solar system's final frontier, is revealing itself as a region of subtle vitality. New crater dating techniques, what they tell us about the early solar system. When humans first looked up at the moon through telescopes, they saw a world covered in scars, craters upon craters, frozen in time. For centuries, those craters were thought to be unchanging, remnants of an ancient era when the solar system was young and chaotic. But in the last few decades, that view has shifted dramatically. New radar and thermal imaging technologies have revealed that beneath its dusty stillness, the moon holds a detailed record of cosmic events stretching back billions of years, and in some cases, it even shows signs of subtle geological activity continuing today. The story of crater dating begins with a simple but crucial question: how old is a crater? Traditionally, scientists estimated ages by counting the number of smaller craters that formed on top of larger ones. The logic was straightforward. Older surfaces accumulate more impacts. By comparing crater densities across different regions, planetary scientists built a relative timeline of the moon's surface history. However, this approach had limits. It provided a sense of older versus younger, but not absolute ages. To anchor those estimates, lunar samples brought back by the Apollo missions were essential. By analyzing radioactive isotopes within rocks from known locations, scientists could match crater densities to specific ages. This calibration became the foundation for dating not only the Moon, but also other rocky worlds across the solar system. Yet as powerful as this method was, it relied heavily on visual observation and manual counting, and the Moon's surface turned out to be more complicated than once believed. The bombardment history of the solar system wasn't uniform. There were periods of intense impacts and long stretches of relative calm. Refining that timeline required more precise tools, ones that could look beneath the surface dust and see how craters had changed over time. That's where radar and thermal imaging revolutionized lunar science. Radar allows scientists to see beneath the top layer of lunar regolith, the powdery soil covering much of the Moon's surface. By bouncing radio waves off the ground and analyzing how they reflect back, researchers can map buried structures, detect differences in rock composition, and even estimate the depth of impact layers. When radar imaging was applied to well-known craters, it revealed that some were not as ancient as previously assumed. Features thought to be billions of years old sometimes showed fresh subsurface layering or signs of recent disturbance. It became clear that small impacts, seismic shaking, and even thermal stress could continue to modify the lunar surface long after the major bombardment had ended. Thermal imaging added another dimension to crater dating. Instruments aboard spacecraft like NASA's Lunar Reconnaissance Orbiter can measure how quickly different regions of the Moon heat up and cool down during the lunar day and night. Freshly formed craters tend to have rougher, blockier surfaces that retain heat differently from older, smoother ones covered in dust. By studying these temperature variations, particularly during the long, cold lunar night, scientists can determine which craters are relatively new. Some of these young craters, less than 100 million years old, suggest that the Moon's surface continues to be reshaped even in recent geological time. This thermal data has revealed surprising details about the Moon's more dynamic side. For instance, the bright crater Giordano Bruno, once thought to be ancient, now appears to be only a few million years old, possibly even younger. Some scientists suggest it may have formed during the time of early human evolution on Earth. The debris from that impact could have briefly affected Earth's atmosphere, perhaps producing meteor storms visible in prehistoric skies. Other craters, like Tycho and Copernicus, show similar signs of youthful heat retention and crisp morphology, indicating that large impacts continued well after the main period of heavy bombardment ended. By refining crater ages on the Moon, scientists have also improved the broader chronology of the solar system's violent youth. The early epochs were dominated by what's known as the late heavy bombardment, a time roughly 4 billion years ago when the inner planets were bombarded by countless asteroids and comets. For decades, the exact duration and intensity of that era were debated. New crater dating methods have helped clarify this picture. Radar and thermal data, combined with updated isotopic analyses from lunar samples, suggest that the bombardment may not have been a single cataclysmic spike, but rather a drawn-out period of smaller impacts tapering over hundreds of millions of years. This has major implications for how and when Earth's crust stabilized enough to support early life. The refinement of lunar crater dating has also had ripple effects for understanding Mars, Mercury, and the distant moons of the solar system. Since crater chronology on these worlds is anchored to the lunar timeline, improved accuracy on the Moon automatically recalibrates planetary ages elsewhere. For example, surfaces on Mars that were once thought to be 3 billion years old may in fact be closer to 2 billion, suggesting longer volcanic or hydrological activity than previously believed. In that sense, each new insight from the Moon acts like a clock adjustment for the entire solar system. Radar imaging has shown that many older craters contain subtle fault lines and collapsed sections, hinting that the Moon's crust is still contracting slightly as it cools. These faults, detected by shadow mapping and seismic modeling, are sometimes found near relatively young impact sites, suggesting that impacts themselves might trigger tectonic adjustments. Even though the Moon lacks plate tectonics like Earth, its surface is not entirely motionless. Small moonquakes, detected by Apollo-era seismometers and confirmed by modern analysis, show that stress still builds and releases occasionally. Every year, countless tiny particles strike the Moon, churning its top layer of soil and exposing fresh material. This process, known as space weathering, gradually darkens and smooths surfaces, masking their true age. But by comparing thermal data with optical albedo, the reflectivity of the surface, scientists can estimate how quickly these weathering processes occur. This has allowed researchers to back-calculate the ages of craters even when they lack sharp physical boundaries. What emerges is a picture of constant, quiet transformation. A surface that looks ancient but is being subtly renewed, grain by grain, over millions of years. The most advanced crater dating techniques now combine multiple layers of data, radar, thermal, optical and spectral, to create 3D reconstructions of impact histories. These composite models show not just when craters formed, but how they degraded over time. In some regions, like the lunar highlands, overlapping impacts create chaotic terrains where the boundaries between individual craters blur. In contrast, the Maria, vast basaltic plains formed by ancient lava flows, preserve impact histories in clearer chronological layers. By comparing these regions, scientists can determine how volcanic resurfacing events interacted with impact bombardment, refining the timeline of both processes. One finding from this work is that the Moon's surface may be geologically younger than once thought in several areas. Some lava plains appear to have solidified only about 1 billion years ago, relatively recent in cosmic terms. That suggests residual volcanic activity lasted much longer than the traditional models proposed. Subtle variations in heat flow and crust thickness could have allowed magma to persist deep underground, occasionally bursting through the surface, even after the main phase of volcanism ended. The presence of such activity means that the Moon's interior retained more warmth, and therefore more dynamism, than previously expected. Crater dating has transformed how we visualize the history of the solar system. Each crater, no matter how small, records an instant of collision, a cosmic event frozen in stone. Some impacts were so massive that they reshaped entire hemispheres, ejecting debris into orbit that later coalesced into new moons or rained down on neighboring planets. Others were fleeting, microscopic impacts that slowly sandblasted surfaces over eons. Together, these impacts form a continuous record of the solar system's evolution. A record that radar and thermal imaging are now decoding with remarkable precision. Modern crater dating techniques are also providing insights into impact processes themselves. By comparing radar profiles of fresh and ancient craters, researchers can estimate how much material was melted, vaporized, or ejected during impacts of different energies. This helps refine models of how atmospheres form and dissipate after bombardment, how planetary crusts mix chemically, and even how volatiles like water and carbon dioxide are redistributed across worlds. On Earth, much of this evidence has been erased by erosion and tectonics. But on the Moon, it remains perfectly preserved, a library of cosmic history only a few days' journey away. Even today, as spacecraft continue to orbit and map the Moon with increasing precision, new craters are being detected forming in real time. Tiny flashes of light captured by telescopes on Earth or impact scars spotted by the LRO show that the bombardment never truly ended. The solar system is still an active shooting gallery, though at a much gentler pace. Each new crater that appears adds another data point to the timeline, another clue in the ongoing story of planetary evolution. Search for biosignatures. Could moons show life-friendly chemistry? One of the greatest challenges in interpreting possible biosignatures is distinguishing life from lifelike chemistry. Nature is efficient at mimicking biology. Processes like serpentinization can generate gases that might otherwise be attributed to metabolism. Ultraviolet radiation can rearrange carbon compounds into complex organics without any biological help. Because of this, scientists are cautious. They seek not just one molecule, but a pattern, a web of relationships among gases, minerals and isotopes that, taken together, defy simple chemical explanation. Isotopic ratios are one of the key indicators. Living organisms tend to prefer lighter isotopes of elements like carbon and nitrogen, leaving a distinct signature in the materials they produce. On Earth, this ratio between carbon-12 and carbon-13 is one of the clearest indicators of biological activity. If a similar pattern were found in the organic compounds on Europa or Enceladus, it would be difficult to explain without invoking life. Missions in the coming decades will carry instruments capable of measuring such tiny differences with extreme precision. If moons can sustain ecosystems independently of their stars, then they might be the most common habitats in the galaxy. Gas giants are frequent, and many are likely orbited by large moons. Even if only a small fraction hosts subsurface oceans, the number of potential biological environments could be staggering. Our solar system, then, may not be special. It may simply be a typical example of a universe where life hides beneath the ice, quietly enduring in the shadows of larger worlds. The upcoming generation of missions marks a turning point. For the first time, we have the technology to test these ideas directly. Europa Kuiper will taste the chemistry of Europa's plumes. Dragonfly will analyze Titan's complex organics. Future missions to Enceladus may one day return samples from its jets. Together, they represent the first coordinated effort to detect not just habitability, but the potential fingerprints of life itself. And while we don't yet know what we'll find, the signs already point toward a cosmos far more alive than we ever imagined. The moons that orbit in silence around distant planets may be more than frozen relics. They may be laboratories of life, where chemistry and time have come together in just the right way to create something extraordinary. Ground-based observatories and adaptive optics, resolving surface features on distant moons. Across the world, as night falls and the air cools, enormous domes turn their gaze toward the heavens. Inside them, mirrors stretch several meters wide, polished to near perfection, while lasers shoot skyward to measure the distortion of Earth's own turbulent atmosphere. These are the modern ground-based observatories, and their technology, adaptive optics, has transformed the way scientists see the distant worlds of our solar system. Once, the flicker of the atmosphere blurred all but the largest and brightest details. Moons beyond Mars appeared as shimmering points of light, their surfaces hidden behind layers of distortion. But today, those same observatories are resolving features once visible only to passing spacecraft, revealing active volcanoes, drifting clouds, and shifting frost patterns from millions of kilometers away. The principle behind adaptive optics is deceptively simple but powerful. As light from a distant object passes through Earth's atmosphere, it bends and warps, distorting the image that reaches the telescope's mirror. By measuring that distortion in real time, using a laser to create an artificial guide star in the upper atmosphere, and then flexing a secondary mirror thousands of times per second to counteract it, astronomers can effectively cancel out the blur. The result is an image so sharp that it rivals those captured by orbiting spacecraft. What once required a probe flying close to a moon can now be achieved from a mountaintop on Earth. This technology has opened an entirely new window into the behavior of the solar system's moons. Take Io, for instance. When Voyager 1 first flew past it in 1979, the sight of erupting volcanoes stunned scientists, but those fleeting images were decades ago. Now, thanks to adaptive optics systems on telescopes like the Keck Observatory in Hawaii and the Very Large Telescope, or VLT, in Chile, astronomers can monitor Io's volcanic activity regularly, even tracking changes over months and years. Bright lava lakes flare and fade, massive plumes rise above the surface, and dark patches spread as molten material cools and hardens. By watching how eruptions move and where new hotspots appear, scientists can infer how the tidal forces within Io's interior shift heat and pressure. It's a way to study planetary geology in real time, without needing to send a new spacecraft every few years. The lava lakes Loki Patera and Pele, for instance, have been repeatedly imaged from Earth with such clarity that scientists can estimate their eruption cycles and the depth of their molten layers. The same technology has brought Titan into sharper focus than ever before. For most of the 20th century, Titan was little more than a golden blur, its dense atmosphere hiding any detail from view. Even the mighty Hubble Space Telescope struggled to see through the haze. But with adaptive optics and new infrared instruments, Earth-based telescopes can now peer beneath Titan's smoggy clouds, revealing changing patterns of methane rain, shifting dunes and patches of surface brightness that appear and fade with the seasons. At observatories like Gemini North and Keck, astronomers have watched Titan's weather evolve across more than a decade, tracking storms that span hundreds of kilometers and drift from equator to pole as the seasons change. These observations have shown that Titan's methane cycle is far more dynamic than once thought. Such data complement the findings from Cassini's mission years ago, helping scientists extend their record of Titan's climate and test models for how such complex systems operate on other worlds. The beauty of adaptive optics is that it doesn't just apply to the largest or brightest moons. Even faint, distant objects, like the icy worlds orbiting Uranus and Neptune, are coming into view. For example, Triton, which has only been visited once by a spacecraft, can be seen to have subtle brightness changes that may indicate frost migration or geyser activity. Seasonal variations in sunlight at Neptune's distance are incredibly slow, unfolding over decades, but Earth-based observatories are now able to capture those changes as they happen. These continuous long-term records are essential. Spacecraft flybys are brief. They offer a snapshot, a moment in time. But the behavior of moons, especially active ones, unfolds over years or even centuries. Volcanoes, ice flows, and atmospheric shifts all change slowly, and only by watching them regularly can scientists build a full picture. Ground-based telescopes, equipped with adaptive optics, fill that crucial role between missions. The data gathered from Earth also guides where to send those spacecraft next. Observations from adaptive optic systems can pinpoint active regions, thermal anomalies, or transient events, helping mission planners decide which areas deserve a closer look. In 2018, for instance, adaptive optics observations helped identify new bright regions on Io that may have marked fresh volcanic eruptions. Those findings informed later studies with Juno. One of the most impressive examples of adaptive optics in action comes from the Keck Observatory's imaging of the Galilean moons. In infrared wavelengths, the telescope can resolve individual features across their disks, all from nearly 600 million kilometers away. The clarity of these images rivals the best that were obtained by Galileo in the 1990s. Combined with spectroscopic data, these observations allow scientists to identify minerals, measure surface temperatures, and detect variations in reflectivity that could signal active processes like frost sublimation or chemical weathering. At the same time, instruments like the Sphere camera on the European Southern Observatory's VLT are pushing the limits even further. Originally designed to detect exoplanets, Sphere's precision optics and coronagraphy techniques can isolate faint moons next to bright planets, revealing details that would otherwise be lost in glare. It has already provided some of the clearest ground-based views of Jupiter's and Saturn's systems ever recorded. By pairing those images with computer models and spacecraft data, researchers can test theories about moon formation, migration, and evolution in unprecedented detail. Even smaller observatories benefit from these advancements. Medium-sized telescopes, once considered too limited for planetary science, can now use compact adaptive optics systems to track changing features on the Moon, Mars, and the larger outer moons. This democratization of technology means that more institutions around the world can contribute to long-term monitoring efforts. The more eyes watching, the better our understanding becomes of how these worlds evolve over time. Beyond the visible and infrared, adaptive optics is also being integrated with spectroscopy and polarimetry, allowing scientists to not only see features clearly but also determine what they're made of. Subtle shifts in light can reveal the presence of frost, organic compounds, or silicate materials. Combined with precise timing, these techniques can even detect transient phenomena such as eruptions, auroral flares, or brief outgassing events on icy bodies. This blending of methods is what makes modern observational astronomy so powerful. To capture an image of a distant moon, knowing that the light you're seeing left that world hours ago and that your telescope has corrected for the turbulence of an entire planet's atmosphere to reveal it clearly, is to touch the edge of human capability. The next generation of telescopes, such as the 30-meter telescope, the extremely large telescope, and the giant Magellan telescope, promises to extend this vision even further. With mirrors larger than anything built before and adaptive optics systems of astonishing sensitivity, they will be able to map surfaces of moons across the solar system with detail comparable to early spacecraft flybys. From the glowing lava of Io to the drifting clouds of Triton and the icy ridges of Europa, these observatories will continue to track how each of these worlds changes with time. In doing so, they will bridge the gap between Earth and the outer planets. Adaptive optics has turned Earth itself into a spacecraft of sorts, an anchored observer peering clearly across the void, recording the restless motion of distant moons as they dance around their planets. Modeling internal oceans, advances in simulating ice rock interfaces. Modern planetary models have evolved from simple sketches of layers into complex three-dimensional systems that simulate the dynamics of entire moons. Each model integrates a dizzying array of variables: gravity, internal heat flow, salinity, density gradients, and tidal flexing. They track how water circulates, how heat rises from the core, and how convection patterns might move material around. When these simulations are run for billions of years of virtual time, they reveal a living world beneath the ice, one that shifts, evolves, and sustains energy. At the heart of these models lies the interaction between liquid water and rock. On Earth, this interaction fuels some of the planet's most fertile environments: deep-sea hydrothermal vents. The models begin with the core's composition. Many icy moons are thought to have silicate or rocky interiors, similar in makeup to primitive asteroids. These cores are not inert. They slowly release heat from the decay of radioactive elements, such as uranium and potassium. In the earliest stages of a moon's history, tidal friction from gravitational interactions with a giant planet like Jupiter or Saturn would have added even more heat. That warmth causes pockets of liquid to form, initiating convection currents that can persist for eons. Computer simulations now show that this internal heating may be self-sustaining. As water seeps into the porous rock, it reacts chemically with minerals, producing hydrogen gas in a process called serpentinization. This reaction releases additional heat, which keeps more water circulating. It's a feedback loop, one that could maintain active hydrothermal systems for billions of years. The discovery that Enceladus is venting hydrogen into space gave these models powerful confirmation. The models predicted it before the data arrived. The next challenge for scientists is understanding how this hydrothermal activity shapes the rest of the ocean above it. Using high-resolution fluid dynamics simulations, researchers can now visualize how plumes of warm water might rise from vents at the seafloor, mix with cooler layers, and form slow-moving convection cells. These currents help distribute heat evenly, preventing the ocean from freezing solid and circulating nutrients throughout its depths. In some simulations, the movement resembles a planetary heartbeat, steady, rhythmic, pulsing through liquid layers that are dozens of kilometers thick. The influence of tides adds another layer of complexity. In the models, tidal heating creates pockets of localized melting, forming temporary reservoirs of water that can drive bursts of activity, possibly even eruptions through cracks in the surface. This would explain the geysers observed on Enceladus and the shifting chaos terrain on Europa. Researchers are using supercomputers to simulate these effects in exquisite detail. They divide a moon into millions of virtual cells, each representing a different temperature, pressure, and material composition. By running the simulation step by step, they can see how heat and motion evolve across vast stretches of time. The results show that even small differences in salt concentration or ice thickness can lead to dramatically different behaviors. Some regions become turbulent and active, while others settle into quiet stability. One of the key findings from recent modeling work is that not all oceans are created equal. Europa's ocean, for example, may be strongly influenced by tidal forces, producing constant internal mixing that brings oxidants from the surface down to the depths. Enceladus's ocean, in contrast, might be more localized, concentrated near the South Pole, where heat and water escape through cracks. Ganymede appears to have multiple layers of ice and water, possibly forming a stacked ocean structure where brine-rich layers alternate with solid ice. These differences suggest that each moon could support very different forms of chemistry. Some of the most advanced simulations incorporate not just physics, but also geochemistry. They track the flow of ions, minerals, and gases between the rock and the ocean, estimating how much material could be exchanged over time. In certain models, hydrothermal circulation can recycle the entire ocean's contents through the rocky core in just a few million years. That kind of turnover ensures a steady supply of nutrients and energy sources, two of the critical ingredients for sustaining life. These models guide real missions. When Europa, Kuiper, and JUICE begin their observations, they will measure magnetic fields, gravity variations, and surface composition. Modelers can predict what those measurements should look like for different internal structures. If the observed data match a certain pattern, it can confirm the presence of liquid layers or active circulation zones. In this way, computational simulations become a map to places we have not yet reached. One fascinating outcome from recent work is the possibility of intermittent ocean vents, regions where the heat flow changes over time, creating cycles of activity and dormancy. In these simulations, the seafloor behaves almost like a living system, responding to shifts in temperature and stress. Over thousands of years, vents might open, flare up, then shut down, only to reignite later. If life exists in these environments, it would have to adapt to this pulsing rhythm of energy availability, perhaps forming resilient ecosystems that can endure long freezes between bursts of warmth. To model these processes accurately, scientists rely on data from multiple sources: the density of the moon, inferred from spacecraft flybys, the surface temperature, measured by infrared sensors, and even tiny wobbles in orbital motion, which reveal the flexibility of the ice shell. Each piece feeds into a broader picture, a living, dynamic simulation that grows more detailed with every new discovery. In recent years, teams have begun to experiment with machine learning algorithms to improve these models further. By feeding supercomputers thousands of variations of initial conditions, researchers can identify patterns that might otherwise be missed. The AI systems learn which combinations of temperature, composition, and tidal stress lead to sustained ocean activity. This approach is already generating new hypotheses. The beauty of these models lies in how they unify different fields of science. Geophysics, chemistry, astronomy, and even biology converge within them. They are not just tools for prediction, but frameworks for imagination, letting scientists visualize the hidden processes that define entire worlds. When a simulation shows hot fluids circulating beneath miles of frozen crust, it invites the mind to picture the seafloor, dark, mineral-streaked, and alive with chemical energy. Each advance in modeling helps scientists decide which moons are worth landing on, where to search for plumes, and what instruments to carry. It narrows down the vastness of the solar system into targets of promise. And though these simulations exist only on screens, glowing in the quiet of computing labs, their implications stretch across light years. In their digital oceans, we can glimpse something universal: the ceaseless exchange between energy and matter, the slow rhythm of planetary evolution, and perhaps the faint mathematical echo of life's possibility beneath the ice. Exomoon candidates, latest from Kepler, K2, and TESS. For all the thousands of exoplanets we've found, the search for exomoons, moons orbiting those distant worlds, remains one of astronomy's most delicate frontiers. It's almost paradoxical. If our own solar system teems with moons, then logic would suggest they must exist elsewhere too. Planets form in disks of dust and gas, and moons are natural byproducts of that process. Yet, when scientists turned their telescopes outward, the evidence proved astonishingly elusive. Spotting a moon around another star is like trying to see a firefly circling a distant lighthouse, both faint, both small, and both hidden in glare. The challenge is not in theory, but in detection. Even with instruments as sensitive as NASA's Kepler Space Telescope, the signals of exomoons are buried deep in noise. Kepler's mission, which began in 2009, revolutionized our understanding of planets by detecting tiny dips in starlight as they transited, passing in front of their stars. But if a planet's signal is faint, a moon's is even fainter still. A large exoplanet might block a fraction of a percent of its star's light, while a moon could dim it by less than 1/100th of that. Distinguishing such a whisper from the background hum of cosmic and instrumental noise requires extraordinary precision. Still, scientists began combing through Kepler's data, looking for anomalies, small timing variations or unexpected distortions in a planet's light curve that could hint at a companion moon. If a planet and moon orbit their shared center of gravity, the planet's transit across the star won't occur at perfectly regular intervals. Sometimes it will appear slightly early, sometimes slightly late, depending on where the moon is in its orbit. This effect, called transit timing variation, or TTV, combined with subtle shifts in the depth or shape of the transit, became the primary clues astronomers hunted for. In 2017, a research team led by David Kipping at Columbia University announced the first compelling exomoon candidate, Kepler 1625 bi. The data came from a single star roughly 8,000 light-years away, hosting a planet about the size of Jupiter. But what drew attention was that the planet's transits showed irregularities that couldn't easily be explained by noise or instrumental error. When the team modeled the system, the best fit included a large moon, possibly as big as Neptune, orbiting the planet at a considerable distance. If true, it would be unlike anything in our solar system. Such a moon, larger than Earth and orbiting a gas giant, would be a new class of object entirely, a supermoon or exomoon giant. Not only would it expand our picture of what moons can be, but it would also open new possibilities for habitable environments. A Neptune-sized moon might have its own atmosphere, clouds or even oceans, warmed not just by starlight, but by reflected light and tidal forces from its host planet. To verify the finding, Kipping's team secured follow-up observations with the Hubble Space Telescope. Hubble's precision confirmed some aspects of the anomaly. The planet's transit timing did indeed deviate in a way consistent with a moon's gravitational influence. Yet the signal was faint and only observed across a few events. Statistical noise and the limited dataset left enough uncertainty that the claim remained unconfirmed. Some in the astronomical community considered it persuasive evidence, others called it premature. But whether or not Kepler 1625 bi ultimately proves to be real, it marked a turning point. For the first time, astronomers had a concrete candidate, something tangible to test and refine their methods on. Then, in early 2022, another intriguing case appeared, Kepler 1708 bi. This time, the analysis drew from both the original Kepler data and its successor mission, K2, which continued operations after Kepler's initial reaction wheel failure. Again, the team reported hints of an additional object orbiting a gas giant, one nearly 2.6 times the radius of Earth, circling a planet itself about 1.5 times Jupiter's size. The orbital configuration, too, resembled that of 1625 bi, a large moon, orbiting far enough to produce measurable timing shifts. What made Kepler 1708 bi particularly fascinating was that the researchers used improved modeling and data processing to reduce the chance of false positives. They simulated thousands of potential scenarios, from star spots to instrumental noise, to see which could mimic the observed signal. The exomoon model still fit best, yet even here, the team remained cautious. With only 2 transits observed, it's impossible to rule out all alternative explanations. The tantalizing possibility of a moon remains just that, a possibility. These 2 candidates dominate the conversation, but they are not alone. Other potential signals have flickered briefly in Kepler's vast dataset, though none have yet withstood scrutiny. Each time, the limitations of data, incomplete coverage, star variability, or noise force astronomers to withhold judgment. Detecting an exomoon requires multiple clean transits, precise timing, and a stable star. The odds of getting all 3, even with thousands of targets, are slim. That's where newer missions like TESS come in. The Transiting Exoplanet Survey satellite, launched in 2018, observes much closer and brighter stars than Kepler did. Its shorter observing windows make it less ideal for detecting long-period planets, but its high precision and broad coverage offer a fresh dataset for exomoon hunting. Already, scientists have started mining TESS data for similar timing irregularities. Unlike Kepler, TESS's targets are close enough for future follow-up by ground-based telescopes or the James Webb Space Telescope, which could detect secondary effects like light reflected from a moon's surface. Still, the challenges remain immense. Moons do not orbit stars directly, they orbit planets. That means their signatures are superimposed on already faint planetary signals. The result is a complex pattern that can easily be mistaken for random noise, stellar activity, or instrumental drift. Moreover, giant exoplanets often have large, diffuse atmospheres that blur the edges of their transits, making small variations harder to pick out. Even if a signal looks promising, distinguishing whether it comes from a moon, a second planet, or a temporary dust ring requires careful modeling and multiple lines of evidence. Despite these obstacles, progress is being made not only through better data, but through better techniques. Machine learning algorithms now help sift through the massive archives of Kepler and TESS data, identifying subtle anomalies that human eyes might miss. Advanced simulations can model light curves with extraordinary detail, accounting for complex gravitational interactions. These tools are refining what once seemed impossible, extracting the faint heartbeat of a moon from a sea of noise. Confirming even a single exomoon would open a new branch of astronomy. Planets were once considered rare until Kepler proved otherwise. Moons could follow the same trajectory. Once the first one is confirmed, scientists expect a flood of discoveries to follow as techniques improve and instruments sharpen. Each detection would reveal something unique about the diversity of planetary systems, how they form, how stable they are, and what kinds of environments might exist for life. Moons are not passive bystanders. In our solar system, they shape planetary climates, stabilize tilts, drive tides, and even harbor oceans where life could emerge. Imagine scaling those roles up to the galactic level. A giant moon orbiting a gas giant in a habitable zone could receive warmth both from its star and its planet, creating conditions unlike any seen on Earth. In some cases, a moon might be more habitable than its planet. These ideas have already inspired models predicting what such worlds might look like. Some simulations suggest that large exomoons could develop dense atmospheres rich in nitrogen or carbon dioxide, shielding their surfaces from radiation. Others propose that tidal heating from their parent planet could keep their interiors warm enough for liquid water, even far from the star's traditional habitable zone. It's possible that the most promising abodes for life beyond Earth won't be planets at all, but moons circling them in graceful, unseen arcs. That possibility has not escaped the attention of mission planners. While Kepler and TESS were not designed primarily for exomoon detection, future observatories may be. Concepts like Plato, the European Space Agency's upcoming exoplanet mission, and NASA's proposed Habitable Worlds Observatory could possess the sensitivity needed to routinely detect moon-sized bodies. With continuous long-duration monitoring and improved photometric precision, these telescopes could capture the delicate interplay of planet and moon with enough clarity to confirm their existence beyond doubt. For now, the story remains one of pursuit and patience. The exomoon search stands where exoplanet science did in the 1990s, filled with speculation, competing interpretations, and a handful of tantalizing signals awaiting confirmation. But the groundwork is being laid. Every refinement in modeling, every new dataset, brings us closer to catching that first definitive glimpse of a moon orbiting another sun. The faint signatures of Kepler 1625 bi and Kepler 1708 bi remain suspended between discovery and doubt. Yet even as their status is debated, they've already transformed the field. Somewhere in those data, amid the noise and uncertainty, there may already be the signal of another moon. Whether it's larger than Earth or smaller than our own moon hardly matters. Its confirmation would mean that moons, like planets, are not unique to our solar system. It would mean that the quiet companionship we see between Earth and its moon is a universal pattern, written into the very architecture of the cosmos. And that idea, even before proof arrives, changes how we imagine the universe, not just filled with planets, but with entire families of worlds dancing in the dark together. Submoons or moonlets. Are there tiny satellites around big moons? Submoons or moonlets represent a further level of cosmic hierarchy: planets orbiting stars, moons orbiting planets, and submoons orbiting moons. It is a structure that, in theory, could continue indefinitely, with each level bound by the same gravitational rules that govern everything from binary stars to planetary systems. But the deeper scientists have looked, the more delicate that balance has proven to be. While no submoons have yet been confirmed anywhere in our solar system, the conditions under which they could exist are now better understood than ever before. The search for submoons begins with the simplest question: is it physically possible for a moon to hold on to something smaller that orbits around it? The intuitive answer seems like it should be yes. After all, if a planet can capture a moon, then why couldn't a large moon, say Ganymede or Triton, capture a tiny rock of its own? But the reality is governed by a delicate interplay between gravitational forces. A submoon would need to orbit within the sphere of influence of its parent moon, known as the Hill sphere, but outside the point where the planet's gravity becomes too strong and pulls it away. That narrow band of stability is remarkably small, particularly for moons that orbit close to their planets. Take Ganymede, for example. If any moon in our neighborhood could host a submoon, Ganymede seems like a likely candidate. But it also orbits Jupiter, whose gravity dominates the local space. The boundary of Ganymede's Hill sphere, where its own gravitational pull overcomes Jupiter's, extends only a few thousand kilometers beyond its surface. That might sound like a lot, but in cosmic terms, it's barely a sliver of room for orbital stability. A submoon orbiting there would have to move quickly and precisely to remain in balance. Any deviation, perhaps caused by tidal forces, radiation, or gravitational nudges from neighboring moons, could easily destabilize it, sending it crashing into Ganymede or out into space. The problem is even worse for smaller moons. Triton fares only slightly better. Despite being larger than our moon and possessing a thick atmosphere, Triton's orbit around Saturn leaves it with limited gravitational territory of its own. Saturn's powerful tides would pull any submoon out of orbit within a few thousand years, an instant compared to the billion-year lifetimes of planetary systems. For moons closer to their planets, such as Io or Europa, the story is even more extreme. Their hill spheres are so compressed by Jupiter's gravity that there simply isn't enough stable space for a submoon to exist at all. In 2018, a team of astronomers led by Juna Kohlmeier and Sean Raymond explored this problem in depth, running extensive simulations to see if any known moons in the solar system could theoretically support submoons. Their results suggested that only a handful of large moons, such as Callisto, Iapetus, and our own moon, might have enough room for a tiny companion to orbit stably for extended periods. Even then, the conditions would be extremely specific. The submoon would have to be small, no more than a few kilometers across, orbiting at just the right distance to avoid tidal disruption. Any larger, and the planet's gravitational pull would quickly tear the system apart. The concept becomes even more complicated when tidal forces are factored in. Tidal effects not only generate heat inside the Moon, but also alter its orbit over time. For a submoon, these forces would be devastating. The parent Moon's tidal bulge would continually drain orbital energy from the smaller body, causing its orbit to decay. Within millions of years, sometimes even sooner, the submoon would spiral inward and either collide with its parent or disintegrate into debris. In a sense, the laws of physics seem to conspire against the long-term survival of such systems. Yet the idea refuses to die, partly because nature often finds surprising ways to defy our expectations. There are a few rare configurations that might allow a submoon to persist. One is the case of a very large moon orbiting a relatively small planet, where the gravitational dominance of the planet isn't overwhelming. Our Moon and Earth fall somewhat into this category. The Moon's Hill sphere extends nearly 60,000 kilometers, theoretically large enough for a small submoon to exist at a safe distance. Some researchers have even speculated that tiny fragments of debris or transient quasi-satellites could occasionally orbit the Moon temporarily, although none have yet been observed to remain stable for long. Another possible case involves distant moons orbiting giant planets far from their stars. For example, Iapetus, which orbits over 3 million kilometers from Saturn, experiences relatively weak tidal forces. Its Hill sphere is much larger than most other moons, perhaps large enough for a submoon to survive. In such an environment, a small captured asteroid or a remnant of the Moon's formation might remain in orbit for millions of years. So far, however, even with high-resolution imaging from spacecraft like Cassini, no such companions have been detected. If they exist, they are either vanishingly small or exceedingly rare. Just as Earth occasionally captures small asteroids for a few months or years before losing them, a large moon could do the same. These transient satellites would be difficult to detect, as their orbits would change quickly, and their size would make them faint even in the best telescopic observations. But simulations suggest that such short-lived companions might occasionally form naturally when a moon passes through regions of dense debris or during impact events that eject material into orbit. Theoretical studies have begun exploring whether submoons could play a role in shaping the evolution of their parent moons. For instance, if a submoon existed early in a moon's history, its gradual orbital decay could produce debris rings, redistribute angular momentum, or even contribute to the resurfacing of the parent moon through impacts. In that sense, even a brief-lived submoon could leave a permanent geological mark. Some have speculated that certain smooth plains or secondary crater chains on large moons might, in principle, record such events, though direct evidence remains elusive. The search for submoons has also expanded beyond our solar system. As astronomers study exoplanetary systems, they've begun to wonder whether exomoons, if confirmed, might themselves have smaller satellites. Around massive gas giants orbiting far from their stars, the gravitational landscape could be gentle enough to allow a large exomoon to hold on to a companion. Some simulations suggest that if a planet-moon pair forms early in a thick circumplanetary disk, leftover debris could coalesce into small submoons before the system stabilizes. If such systems exist, they might resemble miniature versions of solar systems, self-contained worlds within worlds. Detecting a submoon around an exomoon, however, would be almost unimaginably challenging. The signals involved would be orders of magnitude weaker than those used to find exoplanets. Still, the concept of submoons has proven useful in refining models of orbital stability and planetary formation. Each hypothetical layer in the hierarchy adds complexity, forcing scientists to test their understanding of how gravity structures the universe across different scales. The discovery of a submoon would symbolize another step down the ladder of cosmic organization. It would blur the distinction between planet and moon even further, reminding us that the cosmos doesn't adhere to simple categories. In some ways, scientists have already glimpsed hints of this kind of fractal structure. In Saturn's rings, for instance, small moonlets shepherd and shape narrow bands of ice and dust, maintaining order through their gravity. These are not true submoons, since they orbit the planet directly, but they demonstrate how nested gravitational systems can exist on smaller scales. Likewise, some asteroids have tiny satellites of their own, forming binary or even triple systems, suggesting that the concept of moons isn't far-fetched, just uncommon under most conditions. Somewhere in the vast machinery of the cosmos, it's not impossible to imagine a small rock orbiting a larger moon, orbiting a massive planet, orbiting a distant star. The Roman telescope and the era of precision microlensing. In the coming decade, astronomy will enter a new era of precision with the launch of the Nancy Grace Roman Space Telescope. Named after NASA's first chief of astronomy, the Roman telescope represents a bridge between the grand discoveries made by the Hubble and Webb telescopes and the detailed population studies needed to understand our galaxy's hidden structure. While Webb peers deep into time to capture faint galaxies and exoplanet atmospheres, Roman's power lies in its vast field of view and statistical reach. It will not just find individual objects, it will reveal trends, frequencies, and probabilities across millions of systems. The key technique enabling this search is gravitational microlensing, a method that doesn't rely on starlight or planetary transits, but on the subtle bending of light predicted by Einstein's general theory of relativity. When a foreground star passes precisely in front of a more distant background star, its gravity acts like a lens, magnifying the light from behind. If the foreground star hosts a planet, that planet's gravity adds a brief secondary blip to the light curve, a small but distinct signature that reveals its presence. What makes this approach remarkable is that it can detect planets and moons that are otherwise completely dark. It doesn't matter if they're frozen, far from their stars, or even drifting freely through space. Roman's strength will come from both its precision and its scale. It will monitor hundreds of millions of stars toward the galactic bulge, capturing light variations with exquisite accuracy. Each microlensing event is rare and fleeting, lasting days or weeks, and Roman's wide field of view, 100 times greater than Hubble's, will allow it to catch thousands of them in real time. Within that flood of data will lie the signatures of exoplanets down to Earth's mass, and possibly even smaller. When a planet with a moon passes in front of a background star, the combined gravitational field of the two bodies creates a complex lensing pattern. Instead of a single smooth magnification, the light curve can show subtle asymmetries or extra spikes, tiny distortions that betray the moon's presence. These signals are incredibly faint and have so far been beyond the reach of ground-based telescopes. Roman, however, with its stable position at the Earth-Sun L2 point and its ultra-precise imaging system, may finally have the sensitivity needed to distinguish them. In a way, Roman's microlensing survey will function like a galactic census. It won't just tell us where exoplanets and moons are, but how common they might be. Right now, we only have fragments of this larger picture. We know that giant planets often have large moons, that icy satellites around gas giants can harbor internal oceans, and that Earth's own moon plays a vital role in stabilizing our planet's tilt and climate. But we have no idea whether such configurations are typical or exceptional. Is our moon, a single large companion around a terrestrial planet, an oddity or part of a much broader cosmic pattern? Roman's vast data will help answer this question statistically by showing how often such systems occur across the Milky Way. To understand what Roman will look for, it helps to imagine the geometry of a microlensing event. When light from a distant star bends around a nearer star and its planet, the magnification curve can be mapped in great detail. If the planet has a moon, that moon slightly shifts the gravitational balance, producing a secondary magnification that may last only hours. Detecting such a signal requires continuous monitoring, with near-perfect stability and minimal atmospheric interference, something only a space telescope can provide. Roman's design, optimized for wide-field infrared imaging, is uniquely suited to this. Its detectors will capture faint changes in brightness with a precision unachievable from Earth. Because Roman will observe in the infrared, it will also be sensitive to cool, low-mass stars, the kind most common in our galaxy. These dim red dwarfs and their surrounding planetary systems are fertile ground for microlensing studies. Many of the detected events will likely involve planets orbiting such stars at distances where moons could remain stable for billions of years. The mission will therefore probe a region of parameter space untouched by other techniques, complementing the transit and radial velocity methods used by Kepler and TESS. Where those telescopes have revealed the inner architecture of planetary systems, Roman will unveil their distant, colder outskirts. Current theories suggest that moons can form in several ways: through co-accretion in a disk around a young planet, through giant impacts, or by gravitational capture. Each process leaves telltale signs in the resulting mass ratios and orbital characteristics. If Roman detects enough exomoon candidates, astronomers will be able to compare these distributions with those of our own solar system, testing whether the patterns we see here, like the regular icy satellites of Jupiter and Saturn, are universal. A statistical excess of certain configurations could even hint at specific formation mechanisms dominating across the galaxy. While transiting exoplanets must orbit edge-on relative to our line of sight, microlensing is orientation independent. It can reveal planets and moons around stars halfway across the galaxy, even when those systems would otherwise be completely invisible. Some of the most fascinating possibilities involve rogue planets, worlds that drift through space without a star. If such planets retain moons, Roman could, in theory, detect them through brief but distinctive lensing events. These detections would challenge our understanding of how planetary systems evolve and what becomes of moons once their parent planets are ejected from their stellar orbits. The challenge lies not only in detection, but in interpretation. Microlensing signals are inherently ambiguous. Different configurations can produce similar light curves. For example, a binary star system might mimic the signal of a planet-moon pair, or a background stellar fluctuation could distort the apparent brightness pattern. To address this, Roman will work in concert with ground-based networks like the Korean Microlensing Telescope Network, or KMT-ENET, and future adaptive optics facilities. By combining Roman's space-based perspective with observations from Earth, astronomers can reconstruct the geometry of each event in 3 dimensions, breaking degeneracies and confirming the nature of the detected companions. The telescope will continuously monitor the same region of the sky for extended periods, maximizing the chances of catching rare events. Advanced onboard processing will allow scientists to quickly flag promising microlensing candidates and adjust observing strategies in real time. This adaptability is critical because microlensing events cannot be predicted far in advance. They occur randomly as stars align by chance. Once an event begins, it must be observed continuously to capture its full light curve before the opportunity passes forever. By mapping the distribution of planetary and subplanetary bodies, it will provide insight into how matter is structured in our galaxy. It will show where planets are most common, how their formation depends on stellar type, and how gravitational interactions shape their evolution. But within that larger picture, the search for exomoons carries a special weight. While Webb zooms in on individual systems in exquisite detail, Roman will reveal the patterns that tie them together. It is, in essence, the telescope of context, turning isolated discoveries into a cohesive map of what exists. And somewhere in that map may lie the answer to a question as old as humanity's fascination with the moon. Are we typical, or are we rare? If Roman finds that moons are abundant, that large, stable companions commonly orbit planets of all types, it will suggest that systems like ours are the rule, not the exception. That would imply that the conditions that shaped Earth's history, its tides, its stable axial tilt, perhaps even its climate cycles, might play out across countless other worlds. But if the data reveal moons to be scarce, then our own lunar companion may represent a cosmic rarity, a delicate coincidence in a universe full of lonely planets. Either way, Roman's microlensing survey promises to redefine how we think about the structure of planetary systems. Somewhere in those curves may be the first confirmed signal of a moon orbiting a planet hundreds of thousands of light-years away, a distant echo of the relationship that shaped life on Earth. Through Roman's eyes, the galaxy will no longer be an abstract expanse of stars, but a living, intricate network of worlds and their silent companions. When do you think we'll discover the first exomoon? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.